Alright team, today we're going to explore the Linux file system in a simple and practical way. As we go along, you'll see how Linux arranges its files in a hierarchical structure. Then, we'll navigate through directories and practice basic file operations. I'll also show you how to view file contents and understand permissions. So let's get started. Let's first understand how the Linux file system is arranged. Everything begins at the root directory, represented by a single slash. From there, all folders and files branch out like a tree. Let's view the top-level directories. Command, ls/. The ls command is the short form for list and it lists the directory contents. Here, ls/ lists everything under the root directory. You will commonly see /bin, essential commands, /etc, configuration files, /home, user home directories, /var, logs and variable data, /usr, system utilities and libraries. Now that we know the top-level structure, let's check where we currently are. Command, pwd, /home/student. pwd means present working directory. It displays your current working directory in the file system. Now that we know our location, let's move around inside the file system. Command, cd, cd/etc, cd/home, cd ... cd tilde, cd/etc. Go to the /etc directory. cd ... move one level up. cd tilde, return to the home directory. cd simply stands for change directory. Whenever you want to move from one folder to another inside Linux, this is the command you'll use. I am telling Linux, take me to the /etc directory. And notice, there's no actual output on the screen. cd/etc. So, to confirm this, we can run pwd command. When I run pwd, it will show /etc, which means the directory change was successful. Now, moving on, there is a small variation of this command, and that is cd . Here, the ... symbol represents the current directory. To validate it, I can run pwd. So effectively, I'm telling Linux, stay in the same directory. Now let's continue and look at another important variation, and that is cd ... Here, the double dots represent the parent directory, which simply means the folder that is one level above your current folder. cd ... I'm basically telling Linux, take me one step up in the directory tree. To validate it, I can run pwd. And it will show me the new directory, confirming the move. There is another very useful shortcut, and that is cd tilde. The tilde symbol represents the home directory of the current user. So when you type cd tilde, you're telling Linux, take me straight to my home directory. And to check, I can run pwd. And it will show /home/username, confirming that I'm back in my home folder. Let's move forward and see how to view the files and directories inside any location. We use the command ls-l to learn how to view files in a detailed format. ls-l means list in long format. It shows each file and directory along with extra details like permissions, owner, group, file size, and date of modification. This helps us understand what kind of file we're dealing with. You will see multiple columns here. The first column shows file permissions, the second shows number of links, then comes the owner, the group, the size, the date, and finally the file name. If you want to visualize the entire directory structure like a tree, the tree command is very helpful. While ls shows the files in one directory, tree shows folders and subfolders in a branching format. This gives a clear picture of how directories are organized. Command, tree, displays directories in a tree-style visual layout. When you run this, you'll see lines branching out, showing directories, subdirectories, and files under each level. This makes it very easy to understand where things are located and how deep the directory structure goes. After this, we'll perform basic file operations like creating, copying, and deleting. Let's shift our focus to working with directories. And to create a new directory, we use a very simple command called mkdir. mkdir demo_dir. The abbreviation mkdir stands for make directory. This command creates a new folder in the current location. It does not show any output. This can be validated using by ls-l. With ls-l, you will now see demo directory is created successfully. Once directories are created, we should also know how to remove them. And to delete a directory along with its contents, we use the command rm-r demo_dir. rm equals remove. -r equals recursive. This means Linux will delete the folder and everything inside it, including subfolders and files. This is a powerful command, so we must use it carefully because once deleted, the content cannot be recovered. It does not show any output. This can be validated using by ls-l. Now you'll notice that the project directory is no longer listed, which confirms that the directory has been removed. Then we'll create a file. The touch command simply creates an empty file. It does not show any output, but the file gets created instantly. We use the command touch demo_file2.txt. The file will be created. This can be validated using by ls-l. Now you'll see demo_file2.txt listed there, confirming the file was created successfully. Once we have a file, the next operation we usually perform is copying it. For this, we use the cp command. The cp command simply means copy. It takes one file and makes a duplicate of it in the location you specify. cp demo_file.txt copy_file.txt. No output indicates success. This can be validated using by ls-l. You will now see both files, which confirms the copy operation worked correctly. Let's now look at how to move or rename them using the mv command. mv stands for move. It allows you to either rename files or move files from one location to another using just a single instruction. We use the command mv demo_file.txt demo_new.txt. Here, demo_file.txt is the source file. Demo_new.txt is the target name or destination. If both names are in the same directory, this command renames the file. If a directory path is provided, it moves the file to that location instead. The next step is understanding how to delete a file. For this, we use the rm command. rm copy_file.txt. The rm command stands for remove. When we delete a file using rm, it is removed permanently. There is no recycle bin in Linux. No output indicates success. This can be validated using by ls-l. Now you will see the copy file there before. Now it is deleted. The next important step is understanding how to view the contents of a file. So, to read what's inside a text file, we use a simple command called cat demo_file.txt. When I run the cat command with a file name, Linux directly prints everything inside that file onto the terminal. The moment I press enter, the text inside Ubuntu server appears on the screen. There is no extra formatting, no paging. It simply prints the content as it is. If the file is empty, you won't see anything displayed. So team, today we explored the Linux file system and learned how to navigate through directories. We also practiced creating, copying, moving, and deleting files using simple commands. Keep practicing these basics, because they form the foundation of real Linux administration. In this session, we'll explore how Linux organizes storage using partitions and file systems. These are essential skills for managing storage efficiently and ensuring system reliability. You'll learn how to check existing disk layouts, to create and format partitions, to mount them for use, and to make mounts persistent across reboots. Step 0. Switch to root user. You switch to root user to perform disk modifications, because they could affect the entire system and require administrator-level access. We use sudo-i to start an interactive root shell, so we don't need sudo for every command. Meaning, sudo equals superuser -i equals interactive root shell. Sudo-i requires your user password. So, I give my password now. Validate using whoami. Output explanation, prompt changes to hash and whoami returns root. Step 1. Identify disks. lsblk is a command that lists all available block devices, such as disks and partitions, in a tree-like structure. It helps us find free disk for partitioning. Output explanation, shows name, size, type, mount point. Example /dev/sda/dev/sdb. Step 2. Create partition. fdisk is a command line utility used to create, view, and manage disk partitions on Linux systems. Inside fdisk, m shows the help menu. N creates a new partition, P selects a primary partition, Enter accepts default start/N sectors. You can specify a size, example +1G, when prompted. Finally, W writes all changes to the disk. Step 3. Format partition. Formatting a partition prepares it for use by creating a structure that can store files. The mkfs command performs this formatting by building a specific file system, like ext4 or xfs, on the selected partition. Meaning, mkfs equals makefile system. This can be verified using file-s command. If you give file-s/dev/sdb1, output explanation shows file system creation. File-s confirms extension for. Step 4. Temporary mount. Mounting means attaching a storage device or partition to a specific directory, so it becomes accessible in the file system. Until a device is mounted, its data cannot be viewed or used by the system. Now we will create mount point and attach partition temporarily. mkdir creates a new directory to serve as a mount point, and mount attaches a partition to that directory so its contents can be accessed. In Linux, /mnt is a standard directory used as a temporary mount point for file systems or storage devices. So first command is mkdir/mnt/demo. This doesn't give any output. So this means creating a directory is successful. Next command is mount/dev/sdb1/mnt/demo. This command is mounting the /mnt/demo directory in /dev/sdb1. This can be validated using lsblk. Output shows sdb1 partition is mounted with /mnt/demo directory. Step 5. Unmount. Unmounting a partition detaches it from the file system hierarchy, ensuring no processes are using it so the device can be safely removed or modified. This is done using the unmount command, which prevents data corruption by stopping read/write operations to that partition. To unmount a partition in Linux, you use the umount command, which prevents data corruption by stopping read/write operations to that partition. To unmount a partition in Linux, you use the umount command. umount/mnt/demo. Umount detaches the partition from the Linux file system. This can be validated using lsblk. Here sdb1 partition can be seen without any mount points. Step 6. Persistent mount. A persistent mount ensures a partition is automatically mounted at boot, so it's always available without manual mounting. To configure this, you edit the /etc/fs tab file, which defines the devices, mount points, file systems, and options for automatic mounting. Add entry in /etc/fs tab for auto-mount at boot. Save the file. Mount -a. -a option in mount means mount all file systems listed in /etc/fs tab that are not already mounted. Output explanation, mount -a returns no error if entry is correct. Step 6. Verify. Reboot the system and use df-h or lsblk to confirm the partition is automatically mounted at the correct mount point. Always validate with lsblk and df-h after each step. Test persistent mount with mount -a before reboot. Unmount before deleting a partition, umount /mnt/demo. In this demo, we walk through how Linux creates, formats, and mounts partitions for organized storage. You now know how to set up both temporary and persistent mounts using the right tools. With these basics, you're ready to manage disks confidently in any Linux system. Welcome everyone. Today we'll learn about Linux Logical Volume Manager or LVM. Unlike traditional partitions, LVM gives us flexibility to resize, add, or remove storage without downtime. It uses three components: physical volumes, PV, volume groups, VG, and logical volumes, LV. LVM is widely used in enterprise systems for reliability and scalability. By the end of this session, you'll know how to set up LVM, troubleshoot issues, and automate tasks. Step 0. Switch to root user. You switch to root user to perform disk modifications, because they could affect the entire system and require administrator-level access. We use sudo-i to start an interactive root shell, so we don't need sudo for every command. Meaning, sudo equals superuser do, -i equals interactive root shell. Sudo-I requires the user password. So, I give my password now. Validate using whoami. Output explanation, prompt changes to hashtag and whoami returns root. Step 1. Identify physical storage devices. First, let's check what disks are available on our system using lsblk. lsblk shows device names, sizes, and mount points. We can see the disks like SDB, SDC and SDD are free for LVM. Do ensure these disks are unmounted and available. Step 2. Create physical volumes. Convert raw disks into LVM-ready physical volumes using pvcreate. pvcreate/dev/sdb/dev/sdc initializes both disks SDB and SDC as physical volumes for LVM. This prepares the disks to be added into a volume group so they can be managed collectively. pvcreate produces a confirmation message for each disk, such as physical volume/dev/sdb successfully created. Physical volume/dev/sdc successfully created. Check with PVS to confirm PV creation. PVS meaning physical volume scan. PVS shows the device name, volume group it belongs to, physical size, and how much space is free or allocated on that physical volume. Step 3. Create volume group. Creating a volume group combines multiple physical volumes into a single storage pool that LVM can manage flexibly. Combine physical volumes into a volume group using vgcreate. vgcreate creates a new volume group named demo_vg by combining the two physical volumes /dev/sdb and /dev/sdc. The output of vgcreate usually includes a confirmation like volume group demo_vg successfully created. The vgs command will show a one-line summary of the new volume group demo_vg, including how many PVs it has, its total size, and how much free space is available. Step 4. Create logical volume. lvcreate is used to create a logical volume from a volume group, allocating storage space for use as a formatted and mountable partition. This command creates a logical volume named -n my_lv with a size -l of 10 GB inside the volume group demo_vg, making it ready for formatting and mounting. Displays LV name, size, and attributes. Confirm LV creation with LVS. Running LVS after creating the LV will display a summary line showing demo_lv, its size, 10G, and the volume group, demo_vg, it belongs to, confirming that the logical volume was created successfully. Step 5. Format and mount. Now, we need to format the logical volume to create a file system on it, and then mount it to a directory so we can access and use its files. mkfs.ext4/dev/demo_vg/demo_lv creates an ext4 file system on the logical volume so it can store files. mkfs output shows that an ext4 file system is successfully created on the logical volume, including block count, UUID, and journal creation. mkdir/mnt/data creates the directory that will act as the mount point. mkdir creates the mount directory, and the absence of output means it succeeded without errors. Mount/dev/demo_vg/demo_lv/mnt/data attaches the logical volume to the mount point so we can access it. Mount attaches the logical volume to /mnt/data, and no output indicates a successful mount. lsblk verifies the mount by showing the logical volume with its mount point. lsblk verifies the mount by listing all block devices and showing the logical volume with its mount point. Step 6. Extend volume group. vgextend is used to add a new physical volume, PV, to an existing volume group, VG. This increases the total storage capacity of the VG so that more logical volumes can be created or existing ones extended. To extend a volume group, you must first prepare the new disk or partition so LVM can use it. LVM does not work with raw disks directly, so the device must be initialized as a physical volume, PV, before it can be added to a volume group. You start by identifying the new device using lsblk. This partition is then converted into a physical volume using pvcreate/dev/sdd. Validate using PVS. VG extend demo_VG/dev/SDD. This command adds the physical volume/dev/SDD to the volume group demo_VG, expanding the available free space inside the VG. Shows confirmation that the PV has been successfully added to the VG, sometimes including updated VG size and free space. Check the updated volume group details using VGS. After VG extend, a new PV/dev/SDD has successfully joined the VG. And V size is increased. With this workflow, PV create VG extend VGS validation. The volume group is now expanded and ready for further LVM operations. Today, I'll walk you through how Linux detects disks and how RAID 1 ensures data redundancy. We will identify free disks, create a RAID mirror, and verify its status. All steps will be done on Ubuntu Server 22.04 running in VMware. Step 1. Identify available disks. To begin, we identify disks. This command lists all blocked devices in the system. We look for unused disks such as SDB and SDC. They should show no partitions or mount points. Moving on, we install MDADM. MDADM means Multiple Disk and Device Administration. This tool creates, manages, and monitors RAID arrays. Once installed, we can build our RAID device. After that, we create RAID. We use MDADM, create to create RAID array. --level equals 1 means RAID 1, the mirroring level. Every write happens on both disks, SDB and SDC. /dev/md0 becomes our new RAID device. Press yes and the system automatically starts syncing the drives. Up next, we check status. /proc/mdstat is a virtual file showing RAID activity. It displays MD0, active disks, and sync percentage. This confirms RAID creation and healthy state. Continuing on, we format RAID. This creates an ext4 file system on the RAID device. Now MD0 is ready for storing files. Works exactly like formatting a normal disk. Following that, we mount RAID. First, we create a mount point directory. Then we mount the RAID array there. Now users can access files inside /mnt/raid1. Finally, we validate mount. LSBLK now shows MD0 mounted at /mnt/raid1. This confirms the RAID is active and usable. Validation complete. So that completes our RAID 1 hands-on demo. You saw how to identify disks, build a RAID mirror, and check its health. You also learned where to check live RAID status using /proc/mdstat. These commands form the foundation for real-world Linux admin work. Thank you for following along. Practice these steps to master RAID. Today, we are going to learn how to configure network interfaces in Ubuntu Server. This is a very important admin skill, because without network connectivity, servers cannot communicate. We'll explore commands, configuration files, and practical network setup step by step. Now let's start with first step. IPA. IP is the main Linux utility for managing network settings. A or address stands for address. It tells Linux to display IP address information. So, if you press enter you can see ENS33 as the interface name. Up or down as the status. INET IPv4 address. INET6 IPv6 address. Next, to enable or disable an interface we run iplink command. iplink is a basic Linux utility. Sudo iplink set ENS33 up. IP network management tool in Linux. Link we are working with network link layer. Set apply or modify a setting. ENS33 name of the network interface to modify. Up means switch interface on. Press enter, the command is successful. To check this you have to type IPA. Output now appears like ENS33, status state up, meaning network interface is active. Same command can be used to bring the interfaces down by giving sudo iplink set ENS33 down. ENS33 name of the network interface to modify. Turn the interface off or deactivate it. When you run IPA, you will notice ENS33 state is down here, meaning the interface is now OFF. No IP will be assigned, network connectivity will stop immediately. Now let us assign a static IP instantly. The command for that is sudo IP address add 192.168.1.50/24 dev ENS33. This command assigns a static IPv4 address to the interface ENS33 temporarily. IP main Linux tool for network configuration. Address add a new IP address to an interface. 192.168.1.50/24 IP plus subnet mask 255.255.255.0. Dev ENS33 apply configuration to device or interface ENS33. There is no success output. Linux returns silently if the command worked. To verify, run IPA. And here you can see, inet is assigned with IP 192.168.1.50/24 scope global ENS33, which is given in the add address command. After this, adds default gateway for outbound traffic so the system can reach external networks, LAN/internet. The command is sudo IP route add default via 192.168.1.1. IP network command controller. Route adding a new routing rule. Default route for all unknown networks. Via 192.168.1.1 use gateway 192.168.1.1 for outbound packets. Like the previous command, no visible success message, but confirmation comes from IP route. This command is used to view and manage the system's routing table. All external traffic for ENS33 will now go through gateway 192.168.1.1. Next, if we want automate IP from DHCP, assign dynamic IP, DHCP. The command for this is sudo dhclient ENS33. dhclient DHCP client requests network config from server. ENS33 means the network interface that will receive the IP. This command requests an IP address automatically from a DHCP server for the interface ENS33, instead of manually configuring IP. When executed, Linux sends a request to DHCP server asking for IP address, subnet mask, gateway and DNS information. All configuration is applied automatically if a DHCP server is available. Unlike static assignment, this command displays messages like DHCP DISCOVER on ENS33, meaning searching for DHCP server. But we are getting error, IPv4, address already assigned. This message is not a failure. It means the interface already has the same IPv4 address. DHClient requested DHCP again. Linux detected no change as DNCP is requesting the same IP as assigned by netplan, so it reports this informational message. Now that we know how to get an IP automatically using DHClient, it's equally important to know how to release or remove that IP. The command for this is sudo dhclient ENS33. This command dhclient releases the DHCP assigned IP address from the interface ENS33. In this command, dhclient DHCP client program -r release the assigned IP ENS33 interface from which IP will be released. You will usually see messages like killed old client process. To verify the release, run IPA. In the output, you get IP for ENS33. This is because the DHCP is disabled, but the IP address is still assigned via netplan, which uses systemd-networkd as the renderer. When you configure networking temporarily using commands like IP, the settings reset after reboot. To make the configuration permanent, we use nano to modify netplan YAML configuration files in /etc/netplan/01 netf.yaml. Open the netplan config file with nano. Add or edit the network configuration. Example static IP configuration. Starts the netplan network configuration, version 2. Uses systemd-networkd to manage networking, default for Ubuntu server. Defines wired Ethernet interfaces. Specifies the network interface name, VMware default. Disables DHCP, IP will be set manually. Assigns a static IPv4 address with subnet mask. Sets the default gateway for external network access. Starts DNS configurations. Specifies DNS servers for name resolution. To save and exit nano. Press Ctrl+O to save. Press Enter and Yes to confirm. Press Ctrl+X to exit. Now we have modified the file. Next, to apply the configuration, type sudo netplan apply. This command is going to update the configuration. Note, any incorrect indentation will make the network will fail. Now, your network settings are now permanent and will remain even after system reboot. Let's confirm this with IP route. Default route shows the gateway. Confirms network routes. Now, after these executions, we have learnt the kernel interaction with interfaces. A kernel handles packet flow. IP, DH client, netplan only instruct kernel. The communication happens inside kernel space for speed. Great work today, we configured interfaces successfully. And assigned DHCP and static IP using commands and netplan. We validated connectivity and learned real troubleshooting. Now it's your turn. Task 1. Bring interface down, assign static IP, apply netplan. 2. Verify using ping plus IP address. 3. Troubleshoot errors, observe behavior. Practice often to ace your Linux plus practicals and real-world tasks. Hello learners, today we are deep diving into network performance optimization in Ubuntu server. By the end, you will know how to monitor packets, analyze bandwidth, check active connections and test speed. Let's begin understanding Linux networking like real system administrators. To optimize a network, we first observe traffic like a doctor checks heartbeat. We use TCP dump for packet visibility. It shows live packets with source, destination, protocol, port and helps detect unusual traffic, delays or packet drops. Sudo TCP dump -i, ends33. -i, ends33 monitor interface ends33. Sudo obviously to run with admin rights. TCP dump packet capture utility. Press enter and give your password, you are basically watching the network breathe live. Press Ctrl+C to stop the process and you can see. IP type of packet, IP packet. 192.168.x.x source plus destination IP addresses. Port numbers, 443 for HTTPS, 53 for DNS, etc. Size of the packet data capture, loss, etc. You can get a good idea on the activities on the interface ends33. After seeing traffic, let's measure who is using most bandwidth. We will use iftop for real-time bandwidth graphs. To install iftop, type sudo apt install iftop-y. But in my end, it's already installed with the newest version. Then type sudo iftop-i, ends33. Iftop bandwidth monitor. -i, ends33 monitor that interface. This command opens a live dashboard showing who your system is communicating with, and how much bandwidth is being used. Left side IP, your system or other connected devices. Right side IP, remote system/website communicating with yours. Speeds, KB or MB, data sent or received in 2 seconds, 10 seconds, 40 seconds intervals. TX, upload bandwidth usage. RX, download bandwidth usage. TX and RX can be seen at the bottom. Press Ctrl+C to exit. Let's move forward to identifying which services are running and on which ports. For that, we use the command ss-tunap. SS stands for socket statistics. -T shows TCP connections. -U shows UDP connections. -N displays ports in numeric form. -A shows all listening and established connections. -P shows process ID and name using each connection. The output display information about network socket connections, listening ports, and processes. This command and faster and modern alternative to netstat. Now we will run a network speed test like an internal speed test. iperf equals internet performance tool 3 equals version 3. iperf3 works as iperf3-s server. iperf3-c a server _IP client. To install, type sudo apt install iperf3-y. -y for yes. It will ask my password. When entered, you can see it's available in my device. So, move on for the next command. So, next we will test it for server mode. iperf3-s. -s equals runs iperf3 in server mode. When executed, you will see something like server listening on 5001. Meaning, A server is running successfully. It is listening for incoming iperf3 client requests. This command makes your system act as a server, waiting to measure network speed when a client connects. The next step is to test network speed from a client system. Here, I have the server machine on my left-hand side, listening on port 5001 and another machine running as a client on my right-hand side. Now, type iperf3-c192.168.0.106. -c equals runs iperf3 in client mode. 192.168.0.106 being the IP of server machine. When you press enter, client machine connects to the server and sends traffic to the server, or receives, depending on options. And you can see entries on the server for connection with the client IP 192.168.0.106. Measures both client and server's throughput, latency, and transfer rates. This command connects your system to the iperf3 server and measures network throughput between the client and server. Now let's check how DNS caching is performing. Even with good bandwidth, DNS delay slows everything. So, it's useful to check how your system's DNS resolver is performing. Now, we are going to check the DNS cache status using resolve-ctl statistics. Resolve-ctl, command used to query and control DNS resolution on systems running systemd-resolved. A statistics shows runtime statistics about DNS queries and cache usage. When executed, you can see the cache status current. Cache size, number of entries currently cached. A hits, queries answered from cache, faster. The misses, queries that required actual DNS lookup, slower. And the transactions. Current transactions, number of DNS queries currently being processed. Total transactions, total DNS queries processed since system start. Cached DNS equals faster responses. This command tells you how many DNS queries were resolved, cached, or failed, giving insight into DNS performance. Here, the misses are high, meaning latency is more. If cache hits are high, DNS resolution is fast. If cache misses are high, the system keeps asking external DNS servers, which increases latency. Here, we can see. Now, if the DNS is not responding or after modifying DNS resolver settings, we need to apply the changes. For that, we restart the resolver service using sudo systemctl restart systemd-resolved. Sudo run command with administrator privileges. A systemctl tool to manage systemd services on Linux. Restart stops and starts the service again. Systemd-resolve the systemd DNS resolver service. After, authenticated through my password, this command restarts the DNS resolver service on Ubuntu without restarting the system to make your configuration changes effective immediately. There is no output if successful. You can verify the service status with systemctl status systemd-resolved. You can see the DNS is restarted successfully. We captured packets, monitored bandwidth, reviewed connections, and tested throughput. These commands help identify latency, bottlenecks, and slow DNS issues. Till now, we have understood Linux architecture and the boot process. Now let's explore Bash shell scripting, where Linux becomes powerful and automatic. In the next few minutes, I'll demonstrate how to write scripts live and show how Linux can work for us. Let's begin by creating our first shell script file and start writing commands inside it. Nano is one of the simplest and most commonly available editors in Linux. I'll use the nano command followed by a file name. If the file does not exist, nano will create it automatically. nanodemo.sh. Press enter. Now, the nano editor screen opens and I can directly start typing my content. There is no separate insert mode, whatever I type appears in the file. To exit the editor, I press Ctrl+X. If there are unsaved changes, nano will prompt me before exiting. Next we will discuss shebang line, which is very important. The shebang is the first line of a script, which specifies the interpreter for the script. #bin/bash. Hashtag is called the shebang. /bin/bash is the bash interpreter path. Tells Linux to run this script using bash. This line is read before execution. Writing sequential commands means placing commands one below the other in a script. Linux executes these commands from top to bottom, in the same order they are written. Each command runs only after the previous command finishes. Echo hello students. Date. Huami. Echo prints text. Date shows current date and time. Huami shows logged in user. Commands execute from top to bottom. Permissions are very important in Linux, as they make the script executable. Linux will not run a script unless execute permission is given. chmod plus x demo.sh. chmod changes file permissions. Plus x adds execute permission. No output means success. To verify the permission, run lsl-demo.sh, which displays file permissions. Here, x indicates executable, which confirms execute permission for the script file. Next, we can execute the script. To run the script, type ./demo.sh. / means current directory. Script runs using shebang. Displays echo, date, and user as output. Now, we will discuss using variables. Variable stores a value. Course equals Linux plus. Echo, welcome to $course training. Here, course is a variable used to store a value, which is Linux plus. The $course retrieves that stored value when the script runs. This helps us reuse data and avoid hard-coding values in scripts. The output shows Linux plus is substituted in the place of the variable course. Next, we will discuss the scope of variable, global versus local. I type a small script, global_var equals I am global, outside the function. myfunc, created myfunc. Local_var equals I am local, variable inside the function. Echo $local_var, print command inside the function. myfunc, call the function. Echo $global_var, use the global variable outside the function. When you press enter, you can see I am local for local variable and I am global for global variable. Here, global_var is defined outside the function, so it is accessible anywhere in the script. Local_var is defined inside the function using the local keyword, so it is accessible only within that function. This helps avoid variable conflicts and keep scripts clean and organized. Important note: indentation is not required in Bash, but it is considered best practice. Linux interprets scripts using keywords, not spaces. Indentation helps humans read code. Scripts can take decisions using if. An if statement in Bash starts with if and ends with fi. The word fi means end of if, it tells Linux that the condition block is finished. Without fi, the script will fail because Linux won't know where the if statement ends. Now, I give a small script. File equals /etc/password. If $file, then echo file exists. Else echo file not found. Fi. Here, we store the file path /etc/password in a variable called file. The if statement checks whether that file exists using f. If the file exists, it prints file exists, otherwise, it prints file not found. And you can see file exists is printed. When we repeat tasks, for loops help. Now I will write a small script here. For f and /etc/star.conf. Do. Echo $f. Done. This is a for loop that goes through all .conf files in the /etc directory. Each file name is stored one by one in the variable f. The loop starts with for, runs commands between do and done, and ends at done. Do and done define the loop block in Bash. In the output we can see all files ending with .conf inside /etc. The loop runs once for every matching file and echo $f prints the path of the file. Now, we need a loop that waits for a condition, while loop. The script for the same is count equals 1. While $count, $3. Do. Echo, count is $count. Sleep 1. Count equals $count plus 1. Done. Here, this is a while loop that runs as long as the condition is true. Count starts at 1, and the loop runs while count is less than or equal to 3. Inside the loop, it prints the count, waits for 1 second, then increases the count until the loop ends. Here, count equals 1 initializes the counter. While $count, $3, it checks the condition. Echo displays the current value. Sleep 1 pauses for 1 second. Count equals $count plus 1, increments the counter. Done ends the loop. While loops run until the condition becomes false. In the output, you can see count equals 1, count equals 2 and count equals 3. Scripts can also interact with users, using the command, read. Read command is used to accept user input in Bash scripts. Read p, enter your name, a name. Here, read takes input from the user and stores it in a variable called a name. The p option shows a prompt message asking for the name. Echo, hello $a name. Then echo uses the stored value to display a greeting message. Read p asks for input with a message. A name stores what the user types. $a name retrieves the entered value. Comments make scripts easy to understand. In Bash, a comment starts with the hashtag symbol and is ignored by the shell. Comments are used to explain what the code does, not to execute commands. They improve readability and help others understand and maintain the script. Hashtag this is a comment. And this is not executed. Let's combine everything into one real task, a mini practical backup script. Hashtag /bin/bash. src equals $home. dest equals /tmp/backup. Dir p$dest. tar czf $dest /home_backup.tar.gz $src. Echo backup completed. Here, hashtag /bin/bash is the shebang, which tells Linux to run this script using the bash shell. src stores the source directory, which is the user's home directory, and dest stores the backup location. Dir p creates the backup directory if it doesn't exist, tar czf creates a compressed backup file, and finally echo confirms that the backup is completed. The screen displays backup completed if all the commands are successful. This can be validated using ls/lh/tmp/backup/. This command lists the contents of /tmp/backup file, and we should see the backup file we created, home_backup.tar.gz. Common bash scripting mistakes students make. Forgetting the shebang line. Not giving execute permission, chmod +x missing. Using spaces around equals in variables. Forgetting $ while using variables. Missing spaces inside, in if statements. Forgetting fi and done. Hard coding values instead of variables. Not quoting variables. Running scripts without reading them. A script security note. Never run scripts from unknown sources. Always open and review scripts before execution. So, today, you saw how bash scripts automate Linux tasks. With simple scripts, Linux becomes fast and powerful. Practice scripting daily, it's essential for Linux Plus and real jobs. We have already understood Linux architecture and the boot process. Now we move to an important admin task, backups. In this demo, we will automate backups and verify integrity using checksums. Now we move to automation by creating a backup script. nanobackup.sh. Nano is a simple text editor. I'm creating a file called backup.sh. The Nano editor opens, ready to accept commands. Once the script file is created, the next step is to add the required content. The first line tells Linux to use bash. We define variables for source, destination, and date as variables. Tar creates a compressed backup, and immediately after that, we generate a checksum to verify integrity. Save this and exit with Ctrl+O and Ctrl+X. Linux does not allow scripts to run unless we give permission. chmod +x backup.sh. chmod changes permissions and +x means allow execution. No output means permission was applied successfully. Before scheduling, we always test manually. /backup.sh. The / tells Linux to run the script from the current directory. If no error appears, the script ran successfully. Now let's verify whether the backup files are created. ls-lh backups. ls is list. -l shows detailed listing, -h shows human readable sizes. You can see a .tar.gz file with date and time. You can also see a .sha256 checksum file. Creating a backup is not enough. We must verify the file's integrity. SHA-256 some-c backup/backup_*.SHA-256. This command recalculates the checksum and compares it with the saved value. The output, backup_2025-01-01-01-00.tar.gz::OK, means the backup file is not corrupted. Now let's automate this backup to run daily. crontab-e. This opens the cron schedule editor for the current user. Crontab stores scheduled jobs, and each cron entry defines one scheduled task. Now add the cron entry. ****/home/ramya/dmob.sh. Here, 5* means every minute, every hour, every day, etc. This runs the backup every minute. 01***/home/user/backup.sh. Means 0 equals minute, 1 equals hour, *** equals every day, every month, every weekday. This runs the backup every day at 1 a.m. and cron works silently in the background. Now press Ctrl+O for write out and Ctrl+X for exit. Let's confirm that the job is registered. crontab-L. The scheduled backup entry is displayed. Since cron runs silently, logs are very important. cat backup/backup.log. Cat displays file contents. Enter the command and you will see timestamps showing successful backup executions. Now let's look at incremental backups. rsync-av student data /backup /rsync_backup/. Rsync copies only changed files. This saves time and storage. Files being copied are listed. If nothing changed, very little output appears. Backups should not grow forever. Find backups-type f-m time +7. This finds backup files older than 7 days. Now we give it for 7 minutes. Find backups-type f-m min +1 delete. Old backup file names, if there is anything, appear in the output. Today, we automated Linux backups using scripts and cron. We verified backup integrity using checksums. This is a real-world Linux administrator skill and a key Linux Plus topic. So far, we have covered Linux storage and networking in separate parts. Now, let's bring everything together and move into configuring virtual storage and networking. In this demo, I'll show you how to add a virtual disk, configure it in Ubuntu, and explain NAT and bridged networking. Before we begin, let's understand the virtual storage concepts. In virtualization, storage is provided as virtual disks by the hypervisor. Linux treats these virtual disks exactly like physical hard disks, so the same commands apply. Now, let me start by adding a new virtual disk from VMware. I am currently working in the VMware interface of an Ubuntu machine. The steps: 1. Power off the Ubuntu virtual machine. 2. Right-click the VM and select Settings. 3. Click Add. 4. Select Hard Disk and click Next. 5. Choose SCSI, Recommended. Next. 6. Select Create a new virtual disk. 7. Set the disk size to 5 GB. 8. Click Finish and power on the VM. At this point, VMware has attached a new disk, but Linux has not yet used it. Now let's log on, switch to Ubuntu to check if Linux can see the disk. Enter the password. Now let's switch to Ubuntu and check if Linux can see the disk. LSBLK. LSBLK means List Block Devices. It shows all disks and partitions connected to the system. This shows all the disks available in the environment. SDA is OS disk and SDB is another disk attached to the machine, which is the new disk. Step 3. Creating a partition. Next, we must create a partition on the new disk. Command: sudo fdisk/dev/sdb. Fdisk is used to create and manage disk partitions. /dev/sdc refers to the new disk. Inside fdisk. N. Create a new partition. P. Primary partition. Press Enter to accept defaults. W. Write changes. The partition table is updated. Linux can now use /dev/sdb1. Step 4. Creating a file system. Now, we create a file system on the partition. sudo mkfs.ext4/dev/sdc1. Explanation. MKFS means Make File System. Extension 4 is a commonly used Linux file system. Press Enter. Now, file system created successfully. The disk is now ready to store files. Step 5. Mounting the disk. Next, we attach the disk to the Linux directory structure. Enter the following commands. sudo mkdir/data3. sudo mount/dev/sdb1/data3. mkdir creates a directory. Mount attaches the disk to the directory. No output means execution is successful. We can verify this using dfh. The /data directory appears with available for SDB1. This confirms the disk is mounted correctly. Part 2. Virtual networking. Now let's move to networking. Every virtual machine needs a virtual network adapter. For Linux Plus, the most important modes are NAT and bridged. Step 6. NAT networking configuration. First, let's configure NAT networking. Now, I'm again in the VMware interface. VMware steps. 1. Power off the VM. 2. Go to VM settings. 3. Select network adapter. 4. Choose NAT. 5. Power on the VM. Now let's verify this inside Ubuntu. IPA. IPA displays all network interfaces and IP addresses. In the output, you can see the VM receives a private IP address, such as 192.168.x.x. This IP is provided by VMware NAT. Now that we have the IP address, the next thing we must check is how traffic leaves this system. IP route. IP route shows the routing table. In the output, you can see the default route points to a VMware virtual gateway. This means traffic goes through the host system. So far, the configuration looks good. Let's now confirm connectivity with a simple command. Ping c3google.com. Ping checks network connectivity. In the output, if you could see successful replies, it confirms the internet access. As a summary, NAT allows the VM to access the internet, but other systems cannot directly access the VM. Step 7. Bridged networking configuration. So far, we saw how NAT networking works. Now, let's move to bridged networking, which works very differently. NAT hides the virtual machine behind the host. But in the bridged networking, where the VM becomes part of the real network. To configure bridged networking, we must change the VM's network adapter settings in VMware. Now, I'm again in VMware interface. 1. Power off the VM. 2. Go to VM settings. 3. Select network adapter. 4. Choose bridged. 5. Select the active network adapter. 6. Power on the VM. Now that the VM is running in bridged mode, let's verify the configuration inside Ubuntu. The easiest way is by checking the IP address using IPA. The VM now gets a LAN IP address, such as 192.168.1.x. The VM behaves like a physical machine on the network. This confirms that bridged networking connects the VM directly to the physical network. Part 3. Troubleshooting. Now that we have completed the configuration, let's see how to troubleshoot common storage and networking issues. Storage troubleshooting. First, let's start with storage troubleshooting. Whenever a disk is not working, the first thing we check is whether Linux can see the disk. lsblk verifies disk visibility. In the output we can see the new disk is visible. Next, bulkid, this command displays the UUID, which is required for persistent mounts in the stab file. Networking troubleshooting. Now let's move to network troubleshooting. Here also, we follow a simple and logical order. IPA, the first thing we verify is whether the system has an IP address. The output confirms that the network interface is up and has an assigned IP. Having an IP address is not enough, so the next step is to check the routing path. The first command, iproute, shows the default gateway and tells us where network traffic is sent. Finally, once IP and routing look correct, we test actual connectivity. Ping checks connectivity. Successful replies confirm that the system can reach the network and the internet. So during troubleshooting, always remember: check visibility, then configuration, and finally connectivity. Closing note, talk track, 3 lines. In this demo, we added a virtual disk in VMware and configured it in Ubuntu. We also configured and verified NAT and bridged networking. These skills are essential for the Linux Plus exam and real-world system administration. We have discussed Linux architecture and the boot process. Now moving ahead, we are going to focus on user account management, which is a daily Linux admin task. For this demo, I am logged in as the root user, so I will not use sudo. Section 1. Confirm root login. Before doing any user management, first of all, let me confirm which user I am logged in as. This step is important because only root can manage users. Command, who am I? The command displays the current logged in user. If output shows root, we have full admin access. Section 2. Create basic user. Now that root access is confirmed, let's move forward and create a new user account. Running the command, user add student 1. Here, we can use add user also, but it's a friendly wrapper and don't work in all distros. So, I prefer to go with user add. This command creates a user named student 1. Successful execution gives no output. Section 3. Create user with home directory. However, creating a user without a home directory is not best practice. So next, let's create a proper user. Using some options in the command. User add ms/bin/bash student 2. Here, m creates home directory, s sets shell. Press enter. This command leaves no output. Section 4. Set user password. Now that the user exists, the next step is setting a password, using the command. Password student 2. Password means sets or changes user password. Press enter. Password prompt appears. I type the password, but nothing is displayed on the screen. This is normal security behavior. Then I press enter, re-enter the same password for confirmation, and press enter again. If both entries match, password is set successfully. Section 5. Verify user details. Now let's verify where Linux stores user information. For this, we run the command grep student2/etc/password. Grep searches user entry in /etc/password. Press enter. The output shows UID, GID, home directory, and shell. The X is the password placeholder, not actual password, which is stored in /etc/shadow. Section 6. Assign UID and GID. Now I am creating a user and manually assigning IDs. This is commonly done in enterprise environments to maintain consistency across systems. Command to do this is user add u2001 gdev student 3. Here, u sets user ID and g sets group ID. Here, g is a primary group name or ID. Linux accepts both. No output means the command was executed successfully. But Linux internally created the user and assigns the given IDs. Section 7. Modify user properties. We might need to change any one parameter of the user account. To do that, instead of deleting users, admins could modify accounts with the command usermod s/bin/sh student 2. Here, s means set shell and it changes the login shell. No output confirms change. Section 8. Add user to group. Now I am adding an existing user to a group. Permissions are managed using groups. This is how we give users administrative privileges without making them root. Command usermod ag sudo student 2. Here, append and it adds user to sudo group. And g sudo secondary group and it adds the user student 2 to the sudo group. You could see the command options here, but the execution is successful. Section 9. Verify group membership. Verification is required for the above step. Type the command group student 2. This command lists all assigned groups and confirms the user is now a member of the sudo group. Note: always use ag together. Missing a can remove existing group memberships for the user. Section 10. Lock and unlock user. Admins often lock the user accounts instead of deleting them. This prevents the user from logging in, but keeps all files and settings intact. Command for doing it, password l student 2. Here, l means lock and locks the user account. Expected output could be password expiry information changed. Confirms account status is locked. Then for unlocking the user, and make the user can log in again, run the command password u student 2. Here, u means unlock and it unlocks the user account. The output is same again, password expiry information changed. This confirms the status change of the account. To verify this, run password s student 2. The letter P in the output means the password is active and the account is usable. The user can now log in normally using their password. Section 11. Test user login. I am switching from the current user to another user. This allows me to test whether the user account is working correctly. Command su student 2. Here, su means switch user. And hyphen means login shell and loads the user's full environment. This is important as su student 2 switches user without loading environment. Output prompt changes to $login successful. Note, if the account is locked, you will get the output as SU, authentication failure. Section 12, delete user safely. Finally, when users leave and the user no longer needs access, we should delete the account safely and at the same time, remove the user's files. The command is userdel our student2. Here, userdel removes a user account and remove files. This command removes user and home directory. No output means user deleted. Internally, Linux removes the user entry from system files and deletes the user's home directory. But if you get mail spool not found, it means Linux tried to delete the user's mail and home directory, but which does not exist. This is not an error but a warning. But the user is successfully deleted. This can be verified using the command id student2. You will get an output, no such user, confirming the user no longer exists. Today we covered the complete lifecycle of a Linux user account. These commands are real-world admin skills and Linux Plus exam topics. Please practice them to gain confidence. So far, we have learned how to create and manage users in Linux. Now, we will understand how Linux controls access using groups, which is critical for system security. In this demo, I will show you how to manage groups and group memberships step by step. Step 1. Create a new group. Here, I am creating a new group called DevTeam, using the command group add DevTeam. Here, group add is used to create a new group. DevTeam is the group name. No output means the command executed successfully. Linux confirms success silently for many administrative commands. For a quick verification, run grep devteam /etc/group. We'll search for the group name, devteam inside /etc/group, the config file that contains all group details. In the output, devteam is the group name. X indicates group password placeholder. 1004 is the group ID, GID. Last field shows group members, but now we don't have any. Step 2. Add user to group. Next, we will add a user to the devteam group. Here, student1 is the user we want to add. Command usermod ag devteam student1. Here, usermod modifies user account properties. A means append, do not remove existing groups. G specifies the secondary group. Student1 is added to devteam. No output means the command is successful. Step 3. Verify group membership. We can confirm that student1 is added using id student1. The output that shows group shows all groups the user belongs to. And ID displays UID, GID, and group memberships. Step 12. Group and sudo access. Now, let's demonstrate how group membership can control sudo administrative access. Here, I'm adding student1 to the sudo group, which allows administrative privileges. Any user in the sudo group can run commands as the administrator using sudo command usermod ag sudo student1. No output, the command runs silently. Student1 is now a member of the sudo group. This can be verified using id student1. Step 5. Primary versus secondary group. Now, let's check the primary group of student1. Every user in Linux has one primary group by default and can belong to multiple secondary groups. Enter the command grep student1 /etc/password. Here, grep searches for a specific pattern student1 in the file /etc/password. The GID shown here is the primary group. And the secondary groups, like devteam, don't appear here as we check them using ID or groups. Step 6. Modify group properties. Sometimes, we may need to rename a group without affecting its members. Here, I'm renaming the devteam group to DevOps. The users who are already part of the group remain unaffected. Command groupmod ndevops devteam. Here, groupmod command to modify an existing group. ndevops specifies the new name of the group and devteam current name of the group. No output means the group has been successfully renamed. As before, this can be verified using grep student1 /etc/password. Important tip: make sure the new group name does not already exist, or the command will fail. Step 7. Remove user from group. Now, let's remove a user from a group. Here, I'm removing student1 from the DevOps group. This is useful when a user no longer needs access to the group resources. Command. Pasted, d student1 DevOps. Here pasted manages group membership. D removes user from the group. Expected output is removing user student1 from group DevOps. Step 8. List group members. This can be verified using the command to list group members. GetEnt group DevOps. Here, getEnt gets entries from system databases. Group specifies we want group information. In the output, you get DevOps X 1004, where empty last field means no members in the group. Step 9. Verify using /etc/group. Next, we'll verify the DevOps group details directly from the /etc/group file. Using the command grep DevOps /etc/group. Grep helps us quickly find our group in /etc/group file. In the output, we can see DevOps as group name, X for password placeholder and group ID, and the last field empty showing no users are members currently. Step 10. Group permissions on files. Now on the next step, let's see how group membership affects file access. First, I create a shared directory called /shared, using mkdir/shared. Then, I assign the DevOps group as the group owner of the directory and set permissions so that only the owner and group members can access it. Chown DevOps/shared. Chown means change file /directory ownership. DevOps means set group ownership to DevOps, no user change. The colon before DevOps means we are only changing the group, not the user who owns the directory. /shared is the target directory. No output, command executes silently. Now, we'll set the permissions for the /shared directory. chmod 770/shared. Chmod, change file or directory permissions. 770 permission mode. 7. Owner, read, write, execute. 7. Group, read, write, execute. 0. Others, no access. Verify this using ls/ld/shared. In the output, you can see rwx owner permissions, rwx group permissions. Others have no access. Step 11. Test access control. Now, let's switch to the user student1 to test group-based access. Commands. Su student1. We use su to start a login shell, which ensures all group settings are applied correctly and test directory access using. Linux successfully changed the user but couldn't find the user's directory. So, it's showing this running message. cd/shared. Access allowed only if user belongs to DevOps, demonstrating group permissions in action. Step 12. Real-time group update. Let's demonstrate a real-time way to apply group membership without logging out. Using the command nugroup DevOps. Nugroup switches the current shell to a new primary group. DevOps group name to switch to. By using nugroup DevOps, student1 becomes part of the DevOps group for this session, so they can immediately access /shared. User can now access /shared, which can be verified through cd/shared. ls/l. Step 12. Group and sudo access. Step 13. Delete group safely. Finally, let's clean up by deleting the DevOps group. Remember, you can only delete a group if no users have it as their primary group. Now type the command groupdel DevOps. Here, groupdel deletes unused group. DevOps group must not be primary group of any user. I'm getting permission denied as student1 has this as primary group. So, we will delete this user from the DevOps group using pasted d student1 DevOps. And try deleting the group by executing groupdel DevOps. No output now means the DevOps group is removed from the system. Today, we learned how Linux uses groups to control access securely. These commands are essential for both the Linux Plus exam and real-world systems. Practice these steps to gain confidence in managing users and groups. Thank you. Now that we have understood password policies and authentication, let us move into managing file permissions and ownership. In Linux, permissions decide who can access what, and this is a core Linux Plus skill. I will explain everything step by step and test it live. Now I run ls/l to view file permissions in long format. This command shows who owns the file and what access is allowed. ls/list. L, long listing option, displays detailed information about each file and directory. Lists files in long format so we can clearly see permissions, ownership, and other details. In the output, you can see RWRXRX permissions. RWX owner can read, write, and execute. RX group can read and execute. RX others can read and execute. Root file owner. Root group owner. 4096 file size, bytes. Demo file name. The first D shows this is a directory. Next, to continue our demo, let us create a directory where we can test permissions. Run the command. Dir project and project/data.txt. Here, the double ampersand ensures that next command runs only if the first command succeeds. In the first command, dir means make directory. In the second command, is the output redirection operator. It creates a new empty file if the file does not exist. I'm using output redirection operator here to show that redirection itself can create files but won't update timestamp or look for existing files. Press enter. Since there is no output, it confirms the directory and file has been created successfully. Important note, if the directory already exists, dir will display an error message, which helps in identifying permission or naming issues. Next, let us give execute permission to the file owner and observe how permissions change. We use the command chmod u plus x project/data.txt. Here, chmod means change mode, that is file permissions. U refers to the user, owner. Plus means add permission. X means execute permission. This command adds execute permission only for the owner. Press enter. Chmod does not display output when successful. Verify this using ls_l, which shows X in the user permission section. This means the owner can execute this file, while group and others' permission remain unchanged. Now, instead of symbolic mode, let us apply permissions using numeric mode, which is commonly used by administrators. Numeric mode clearly defines permissions and reduces configuration mistakes. Always remember, 4 equals read, 2 equals write, 1 equals execute, add them to get numeric values. Run the command chmod 640 project/data.txt. Here, chmod changes file permissions. 6 read, 4, plus write, 2, for the owner. 4 read only for the group. 0 no permissions for others. This sets permissions in the order user, group, others. The command when entered, gives no output, but can be verified using ls_l project/data.txt, which shows owner can read and write. A group can only read. Others have no access. Now that permissions are set, let us change the ownership of the file and see how Linux tracks file owners. Run the command sudo chown student2 project/data.txt. Here, chown means change owner. Student2 is the new owner of the file. Project/data.txt is the file whose ownership is being changed. Press enter. No output means the ownership change was successful, which can be verified through ls_l project/data.txt. It shows owner is now student2. Ownership controls who own the file, while permissions control what they can do. If you see a permission issue even after chmod, always check ownership using ls_l. After this, let us change the group ownership so this file can be shared with a team. Run the command sudo chgrp developers project/data.txt. Here, chgrp means change group ownership. Developers is the new group assigned to the file. Project/data.txt is the file being modified. It gives no output. Group ownership allows controlled access for multiple users working together. This is commonly used for shared project files. Remember, group permissions apply only if the user is a member of that group. To apply permissions to the entire directory structure, let us use recursive permissions. Run the command chmod r750 project. Here, r means recursive, applying changes to the directory and all files and subdirectories inside it. 750 means 7 owner, read, write, execute. 5 group, read and execute. 0 others, no access. This is commonly used for secure project directories. Recursive permissions save time but must be used carefully to avoid security issues. Now, let us apply a special permission to protect files inside a shared directory. Sticky bit ensures users can delete only their own files inside their directory. It's commonly used for shared directories like /tmp to protect them from accidental file deletion. Run the command chmod 1777 project. Here, 1 sticky bit, special permission, and 777 read, write, execute for user, group, and others. Press E-verify using ls-ld project. The output shows the permissions as drwxrwxrwt. Here, T at the end confirms the sticky bit is set. Next, let us apply another special permission so that files created in this directory follow group ownership automatically. Run the command chmod 2750 project. Here, 2 setched, special permission. 750 means 7 owner, read, write, execute. 5 group, read and execute. 0 others, no access. With setched on a directory, all new files inherit the directory's group, not the user's primary group. Press enter and verify using ls-ld project. The output shows S in the group position confirms setched is enabled. Setched ensures consistent group ownership in shared project directories. Next we will discuss setched observation. Only the file owner or root administrator can set setched. Typically, root sets setched on system binaries that need to be executed by normal users with elevated privileges. Here we say observation because we are only identifying or recognizing that a file has the setched permission set, not applying or changing it. When a file has setched permission, it runs with the file owner's privileges, not the user who runs it. Most commonly, the owner is root. You can see this using the command ls/usr/bin/password. Press enter and if you see S in the user permission field, the answer is setched and allows command to run with owner privileges. Password needs root access to update /etc/shadow. Setched allows normal users to change their password safely. Security note, setched is powerful and dangerous if misused. Never set it on scripts or untrusted files. Finally, let us check the default permission settings that Linux applies to newly created files and directories. Now, type umask. Umask stands for User File Creation Mask. It defines which permissions are removed by default when new files or directories are created. It does not change existing permissions. In the output, you see 0022. 0 special permissions, not masked. The second 0 user permissions unchanged. 2 write permission removed for group. The second 2 write permission removed for others. Umask controls default permissions and plays a key role in system security. Remember a very important wording, umask subtracts permissions, it does not grant them. Security risk. Avoid using 777 in production. Like chmod 777 project/data.txt, which is dangerous in real systems, full access lets anyone modify or delete the file. Closing. Linux permissions protect systems from unauthorized access. Always assign minimum required permissions. These are key Linux Plus exam topics. So far, we have already understood what Linux processes are and how they move between different states. Now, let us shift from theory to practice and monitor active processes on a live Ubuntu server. This demo will show you how administrators observe, analyze, and control running processes in real time. In this demo, first, we'll list running processes. Then, we'll monitor them live and analyze CPU and memory usage. Finally, we'll control process priority, manage jobs, and troubleshoot common issues. Let's start by listing all active processes. Run the command ps-eopid user stat %cpu %mem com. Here, ps process status -e show every process on the system, -o custom output format, pid process id, user owner of the process, stat process state, %cpu/%mem resource usage, com command name of the process, only the command. You can use cmd or args if you need full command with options. In the output, each line represents one running process. This helps us quickly see who is running what, in which state, and how much CPU and memory it uses. Now, let me filter processes by a specific user. Run the command ps-u root. Here, -u root shows processes owned by the root user. This is useful when troubleshooting admin-level processes or security issues. Static output is useful, but now let's monitor processes live. Execute the command. Top is table of processes, real-time. The output has two sections. At the top, we see CPU usage, memory usage, and load average. Below, processes are sorted by CPU usage by default. This helps identify heavy processes immediately. Press P to sort by CPU, M to sort by memory. To make monitoring easier, let's switch to a more interactive tool. To install htop, execute sudo apt install htop. After installation, run the command htop. Htop is an enhanced human-friendly version of top. It supports mouse, colors, and scrolling. In the output, you can clearly see CPU cores, memory bars, and process states, making it beginner-friendly. Use arrow keys to scroll. Color bars show CPU and memory usage. Tree view shows process hierarchy. You can scroll through processes and view resource usage clearly. Now press Q to exit htop and return to the shell. Next, let's understand how processes are related. Run the command pstree-p. pstree shows process tree. -p displays PIDs. This helps identify parent-child relationships, useful for finding orphan or zombie processes. Identifying zombie processes. Command ps-eopid, ppid, stat, comgrep z. Here, zombie state, press enter. Output gives the zombie process. Zombie processes are the child process which are already dead but not cleaned up by the parent process. If there is no output, it means there are no zombie processes right now. That is actually a healthy system state. Before controlling a process, we must find its PID. Run the commands PID of SSHD, pgrep SSHD, PID of shows PID of a running program. pgrep searches processes by name. In the output, these commands quickly give us PIDs required for process control. Important to know that, in Linux, process IDs are assigned in increasing order. For a same process, the process with the smaller PID was created earlier. Next, if a process hangs, we may need to terminate it. First, we will the PID of some command, say, sleep, and use this PID with kill command. Run the command kill-919552. Kill sends a signal. -9 forcefully stops the process. Press enter and no output means the signal was sent successfully. Now that we know how to stop a process, let us verify whether it was actually terminated. Check PS19552. In the output, you can see the process is killed and the command is sleep 300. Now let's control how much CPU a process can consume. Starting a process with priority, we use nice command. Now execute nice-n10 sleep 5. Nice starts a process with priority. -n10 lower priority, range -20 to 19. Sleep 5 makes a process do nothing for 5 seconds. Key concept here is higher nice value equals lower priority. When you execute this command, you can't see command prompt because the command is running in the foreground. The sleep process is active for 5 seconds. The shell is waiting until the command finishes. Important to remember, only the root user can set negative nice values. There is no visible output, but in the background, the process starts with reduced priority. This can be verified using top. In top, look at the NI column to see the nice value. Next, for changing priority of running process, we use the command runice. Run runice-n15 p19524. Here, runice modifies priority of a running process. -p target PID. Output shows old priority and new priority values. So far, we have seen how Linux runs processes in the system. Now, let us understand how the shell lets us control those processes as jobs. A job is a command started from the current terminal. Each job is given a job number, not a PID. Job control works only within the same terminal session. Let us first run a command in the background. Sleep 300 and runs the job in the background. This output has two parts. The number in brackets is the job ID. The second number is the process ID. Now let us list all background jobs. Jobs list active jobs. The jobs command shows all jobs started from this terminal. The output tells which jobs are running or stopped. Remember, jobs is shell specific and it shows only jobs started from the same terminal. Bring job to foreground. FG%1. FG means foreground and %1 is the job number. Press enter. If we execute this, we will get an output as sleep 300. This means sleep 300 is brought to foreground. Now let us stop the job temporarily. To stop a running job, use the command Ctrl+Z. It pauses the job and sends it to the background in a stopped state. In the output, you can see 1 stopped sleep 300. Note that the job is stopped, not terminated. Now, we can restart the stop job in the background. bg%1. The bg command resumes a stop job in the background. The job continues running, and the terminal is free again. The output shows job numbers and status change clearly. Here, the plus means, this is the current job. In real world, this is useful when compiling code or running scripts that take time. We can monitor or resume jobs without opening a new terminal. To observe changes continuously, we use the command watch. Execute, watch-n2ps-eopid stat %cpu %mem com. Watch repeats a command. -n2 interval option. Refresh every 2 seconds. PS. Process status. In the output, we can see the CPU and memory values change in real time. The same table refreshes every 2 seconds. This helps identify busy or stuck processes and is perfect for monitoring performance trends live. Processes and services go hand in hand. For checking services, we use systemctl. Now run the command. Systemctl status SSH. Explanation. Systemctl controls systemd services. Status shows service state and PID. Output explanation. Displays whether the service is running, stopped, or failed. Monitoring active processes helps us understand system performance in real time. These commands allow us to detect issues early and take corrective action. Mastering them is essential for both the Linux Plus exam and real-world server administration. So far, we have manually monitored and controlled Linux processes. Now, instead of running commands every time, Linux can do this work automatically for us. In this demo, I'll show you how to schedule jobs using cron, and systemd timers. We'll start with one-time scheduling, then move to recurring scheduling, and finally see how modern Linux automates tasks using systemd. Let us first understand one-time job scheduling. Once that is clear, recurring scheduling becomes very easy. We will start with the simplest scheduler. The command is used when a job should run only once, at a specific time. Execute, at now plus 2 minutes. The command is used to schedule a job that runs only once. Press enter and we are now on editor, where you can type the command. Execute an example job after this. ps-eopid, com, %cpu, %mem. -e, every process, -o, output format, PID. Process ID, com, command name that started the process, %cpu. Percentage of CPU utilized by the process, %mem. Percentage of memory utilized by the process. All these fields help in performance monitoring and troubleshooting. Output redirection. Append, /home/student/add_process.log, log file where the process information is stored. This command captures a snapshot of all running processes, including their PID, command name, CPU usage, and memory usage, and appends the information to a log file located at /home/student/add_process.log. Press Ctrl-Z. There is no immediate output. After 2 minutes, Linux runs the job automatically. This is useful for delayed system checks. Before moving ahead, always verify your scheduled jobs. ATQ. It's a short for ATQ and part of the scheduling utility. Shows one-time scheduled jobs scheduled using that have not yet executed. In the output, it shows job ID, scheduled execution time, user who scheduled it etc. Now that you understand one-time scheduling, let us move to recurring job scheduling using cron. Cron is used to schedule tasks that run repeatedly. We have already covered it in previous demo. We just see an example cron entry. To create an cron job, run the command crontab-e. Always confirm your cron jobs using the command crontab-l, which lists active cron jobs for the current user. If a scheduled job fails, logs are the best place to investigate. Let us now check execution logs. Run the command journalctl-u-cron. Here, journal will view logs and -u-cron logs related to cron service. Job execution status. Errors like permission or command path issues. Now, let us see why some commands work in terminal but fail inside cron. Cron runs with a minimal environment. Variables like path, home, and user may not be available. So, we must define environment variables explicitly. For example, if you add date, cron-env.log. In cron tab and execute, it will give error, as cron cannot find date due to limited path. We fix this using environment variables, define path inside cron tab in the correct way as path equals /usr/bin:/bin. Here, path defines command search path for cron and file /tmp/cron-env.log gets updated every minute. This is the safest way to write cron jobs in production. With this, You now understand why environment variables are critical in scheduled tasks. We can use custom environment variables also in cron jobs by adding a custom variable in cron tab. For example, my name equals Linux student. Echo hello my name. My name custom variable and $my name variable expansion during execution. We can always validate the execution order with logs. Next, let's move into modern automation by using systemd timers for more reliable and integrated task scheduling. Ubuntu uses systemd, and systemd timers are the modern way to automate tasks. They are more reliable than cron and work closely with services. Run the command systemctl list timers. This command displays active systemd timers and their schedules. In the output, you can see next for next scheduled time the timer will trigger, last for last time the timer was triggered, left for time remaining until next run, etc. And you can see 13 timers are listed. Now, we will check timer system status using the command systemctl status timers.target. Here, timers.target parent target for all timers. If the output shows active, it confirms systemd timer infrastructure is running. Now that we can schedule tasks, let us see how Linux controls which task runs first. Some tasks must run only after another task completes. Cron handles order by time, but systemd handles order by dependencies. We will test both. Open crontab by running crontab-e and edit the entries as. This means sleep 10 delays second task and ensures step 1 runs before step 2 and run next command only if previous succeeds. This works, but it is not very reliable for complex systems. Now let us see how systemd handles dependencies properly. This is how real servers manage task order. Systemd clearly understands task relationships. Run this command to shows how timers depend on system targets. Systemctl list dependencies timers.target. The output displays execution hierarchy and confirms which timers start first. Always remember, in systemd, if the first task fails, the dependent task will not start. This is not possible in cron but fully supported in systemd. So today, we saw how cron handles recurring jobs, how it schedules one-time tasks, and how systemd timers manage reliable automation. We also verified job execution using cron logs and understood why environment variables and absolute paths are critical. With this, you can confidently schedule, validate, and troubleshoot automated tasks in real servers. Till now, we learned how to install and manage Linux packages. Now we'll see how Linux keeps itself secure using system-wide updates and patches. In this demo, I'll show you manual updates, automatic patching, and verification steps. Before updating anything, the system must first check what updates are available. Execute the command sudo apt update. Here, apt advanced package tool. Update updates the package index. Sudo superuser do. Press enter. This command checks Ubuntu repositories for available updates. It does not install any packages. In the output you can see, and all packages are up to date. Now that the system knows what updates are available, let's apply all system and security patches. Run the command sudo apt full upgrade. Here, apt advanced package tool. Full upgrade performs full system upgrade and resolves dependencies. Sudo superuser do. Press enter. This command installs all system updates including security patches. It can add or remove packages if required. In the output, you can see packages to be upgraded, installed, or removed. But here you see 0 upgraded, 0 newly installed, 0 to remove and 0 not upgraded as the machine is up to date. Important warning, never run apt full upgrade if apt update shows errors or warnings. After applying updates, we should also know how to recover if an update causes a problem. If an update causes issues, rollback can be done by downgrading packages or restoring a VMware snapshot. Always take backups before patching. Manual updates are not practical every day, so let's enable automatic security patching. Run the command sudo dpkg reconfigure unattended upgrades. Here, dpkg Debian Package Manager. Reconfigure reruns configuration wizard. Unattended upgrades, automatic security updates. Explanation. Enables automatic installation of security patches. In the output, The system opens the configuration process and asks whether automatic security updates should be enabled. Choose Yes to enable automatic updates, No to disable them. When you press Yes, you can see replacing with new version means the system is updating the automatic updates configuration file with a new version. But here no output again means the packages are up to date. Before installing or trusting updates, admins often review what exactly is being fixed. Run the command apt changelog openSSL. Here, apt advanced package tool. Changelog displays update history. OpenSSL example package name. This command shows bug fixes and security vulnerabilities including CVE details. The output tells us what was fixed in this package. CVE numbers mean security vulnerabilities. Admins read changelogs to decide how urgent an update is. Press Ctrl+C to exit. After updates are applied, the final step is to verify everything using system logs. Run the command journalctl unattended upgrades. Here, journalctl system log viewer. Filter logs by service. This command is used to verify update success and detect errors. Press enter. In the output, you can see boot, meaning start of logs from a previous system boot. Started unattended upgrades shutdown means the unattended upgrade service started successfully. Deactivated successfully means the unattended upgrade service finished its work without errors. Line 748 means end of log. Now, this implies the automatic security updates are enabled and working normally. So, with updates applied, automated, and verified, our Ubuntu system is now fully patched and secure. Now, we will see some best practices. Schedule updates during low usage hours. Test edit patches before applying in production. Use automation tools for multi-node systems. Today we learned how Linux systems stay secure using patch management. We covered manual updates, automation, and verification. These skills are important for the Linux Plus exam and real-world administration. Now that we understand containers and runtimes, let's move to managing container images and registries. In this demo, I'll show you how images are created, versioned, and shared. These steps are important for the Linux Plus exam and daily admin work. To begin with, the first thing we always do is check whether Docker is already available on the system. This helps avoid duplicate installations and confirms the current environment state. I'll start by running the command docker version. Before we run any Docker command, we need instructions to build an image. These instructions are written in a Docker file. Docker does not magically know what to install or run. So we give Docker a set of instructions in a file called a Docker file. By default, it must be named Dockerfile, capital D. This file tells Docker how to build our custom image. You can think of it as a recipe that tells Docker what to install and what to run. First, go to a working directory. mkdir nginx image, cd nginx image, create a Docker file. Notice there is no extension. Nano Docker file. Now, we are in the editor tab of Docker file, add this content inside the file. From Ubuntu 22.04, run apt update and an apt install y nginx. cmd nginx g daemon off. In this command, from Ubuntu 22.04, tells Docker to start with the official Ubuntu 22.04 image. Run apt update and an apt install y nginx. This installs nginx inside the image. cmd nginx g daemon off. This tells the container what to run when it starts. Starts nginx and daemon off keeps nginx running in the foreground. We can't just run commands directly, as the containers are built from images, and images need build instructions. Now that the Docker file is ready, the next step is to make sure the base image is available locally. For that, I'm using the docker pull command. This command downloads the Ubuntu 22.04 image from Docker Hub, which is a public registry. If the image already exists locally, Docker will not download it again. Docker pull Ubuntu 22.04. Here, Docker CLI. Pull, download image. Ubuntu, image name. 22.04, version tag. In the output, you may hear pull complete or downloaded newer image. Remember this, Docker pull is used to download images from registries, not to run containers. Once the base image is available, we can now build our own custom image. Now I'm using the docker build command. This command reads the Docker file from the current directory and builds a custom image. The T option helps us name the image and assign a version. Docker build t-mynginx 1.0. Here, build, create image, T, tag image, mynginx, image name, 1.0 version, current directory. Each Docker file step executes. Image build success message. Output shows messages like Step 1/3, from Ubuntu 22.04. Step 2/3, run apt update. Step 3/3, cmd, nginx, g, daemon off. At the end, Docker confirms the image was built successfully. After building the image, it's always a good practice to verify it. Run the command. Docker images. In this command, images, list local images. In the output we get repository name, tag version, image ID, and image size. Instead of using Docker Hub, we will create a private registry locally. This registry behaves exactly like Docker Hub, but it runs locally. Run the command. Docker run -d-p 5000:5000 name local, registry 1 registry 2. Here. Run, start container. -d, detached mode. -p, port mapping. --name, container name. Registry 2, registry image. In the output, Docker prints the container ID, which means the registry has started successfully. Registry container runs in background. Listens on port 5000. Verify it is running using Docker PS. Before pushing an image, we must tag it using the registry address. This tells Docker where the image will be pushed. Does not create a new image. Adds an additional tag pointing to the same image and prepares it for pushing to the local registry. Docker tag mynginx 1.0 localhost 5000/mynginx 1.0. Here. Tag, create new reference. Localhost 5000, local registry address. No output means the tagging was successful and the image now has 2 tags. Now we push the image into our private registry. Docker push localhost 5000/mynginx 1.0. What this command does is, uploads the image layers, stores them in the local private registry, makes the image available for other systems or future polls. If you get an output referring to repository, push is completed successfully. Over time, unused images consume disk space and must be cleaned. To remove a specific image, run the command. Docker rmi mynginx 1.0. Here, rmi remove image. Deletes only the selected image. Now we remove dangling images. Enter the command, docker image prune. This command removes unused, untagged images and frees disk space safely. Press Y. And now the image is deleted successfully. Now that the image is ready, the next step is to authenticate before pushing it. Run the command, docker login. In this command, login. Authenticate to registry. Prompts for credentials. After you enter them, in the output you can see login succeeded message. After authentication, we can now upload the image to the registry. Run the command. Docker push ramiasavam/mynginx 1.0. Here. Push, upload image. Username, registry namespace. mynginx, image name. 1.0, version tag. Uploads layers. The output confirms successful push, but here I get image does not exist error as we cleaned the images before. To summarize, we created, tagged, and pushed container images using registries. This ensures consistent and reliable application deployment. Practice these steps to be exam ready and job ready. Now that we know container images, let's see how containers talk to each other and store data. In this demo, I'll show you Docker networking and storage using simple, real commands. Please watch the terminal carefully as I run each command. As a first step, we create a bridge network that containers can use to communicate. Run the command. Docker network create demo_bridge. Explaining. Docker network works with Docker networks. Creates a new network. Demo_bridge name of the network. This command creates a custom bridge network. Containers connected to this network can communicate with each other. In the output, a network ID is displayed, confirming the network is created. This output confirms the network was created successfully. Now that the network is ready, let's run a container and connect it to that network. Execute the command. Docker run -d -name web1 network demo _bridge nginx. Explaining this, Docker run starts a new container. -d runs the container in the background. --name web1 gives the container a name. --network demo _bridge connects it to the bridge network. Nginx image used to create the container. The command runs a container named web1 and connects it to the bridge network. In the output, a container ID is displayed, showing the container is running. This container is now part of the demo _bridge network, so it can communicate with other containers on the same network. To clearly see container communication, let's run one more container on the same network. Run the command, docker run -d -name web2 network demo _bridge nginx. Explanation: this Docker run starts a new container. -d runs in the background. -name web2 names the container. -network demo _bridge connects it to the same bridge network. Nginx image used. This command runs a second container on the same bridge network. This demonstrates container-to-container communication. In the output, you can see a second container ID is displayed, confirming the second container is running. Now both Web1 and Web2 are on the same bridge network, so they can communicate with each other internally. Now let's make the container accessible from the host by exposing a port. Run the command, docker run -d -name web3 network demo _bridge -p8080:80 nginx. Explaining the syntax, Docker run starts a new container. -d runs in the background. -name web3 names the container. -network demo _bridge connects it to the bridge network. -p8080:80 maps host port 8080 to container port 80. Nginx image used. This command maps container port 80 to host port 8080, allowing external access. A container ID is displayed in the output. We can test the connectivity by opening a browser and accessing http://localhost 8080. The Nginx welcome page confirms successful port mapping. Next, let's look at a different networking mode called host networking. Run the command, docker run -rm -network host nginx. Here, Docker run starts a new container. -rm removes the container automatically when it stops. -network host uses the host's network stack. Nginx image used. This command runs a container using the host's network directly. No port mapping is required in host network mode. After executing, the container starts and binds directly to the host network. In host mode, the container shares the host's network, which is faster but provides less isolation than bridge mode. Now let's inspect the network and see how the containers are connected. Run the command, docker network inspect demo _bridge. Explanation: Docker network works with Docker networks. Inspect displays detailed configuration. Demo _bridge name of the network being inspected. This command displays detailed network information such as network driver, connected containers, IP address assignments. This confirms which containers are attached to the network. Finally, let's attach a persistent volume so that data remains even if the container stops. Run the command, docker run -d -name data _test -v demo _volume /usr/share/nginx/html nginx. In this syntax, docker run starts a new container. -d runs in the background. -name data _test names the container. -v demo _volume /usr/share/nginx/html mounts the volume. Nginx image used. This command attaches a Docker volume to the container. Data stored in this location remains even after container restarts. In the output, a container ID is displayed. Docker confirms the volume is attached and data is retained after stopping and restarting the container. Now that the demo is complete, let's clean up the containers, network, and volume we created. Cleanup is a good practice after every demo or lab to keep the system clean and avoid conflicts. To stop and remove all demo containers, docker rm-f web1 web2 web3 data _test. This command stops running containers and removes them from the system. In the output, container names are listed as they are removed. Web1 web2 web3 data _test. Next, to remove the bridge network, run the command, docker network rm demo _bridge. This command deletes the custom bridge network. In the output, the network name is displayed, confirming removal. Finally, to remove the volume, Docker volume rm demo_volume. This command deletes the Docker volume created for the demo. In the output, volume name is displayed confirming the delete. Container networking controls how containers communicate. Volumes ensure data persistence across container restarts. These commands are essential for the CompTIA Linux Plus exam. Now you can practice these hands-on exercises. Create a bridge network. Run 2 containers on that network. Expose one container port to the host. Attach a volume to a container. Thank you. Now that we understand container images and security, let's move to the container lifecycle. In this demo, I'll show how a container is created, managed, paused, restarted, scaled, and removed. Please focus on what each command does, not memorizing everything. First, I am creating a container using the Docker CLI using the command docker run -d name web1 nginx. Here, docker run create and start container. -d detached mode runs it in the background. --name web1 name for easy identification of the container. Nginx lightweight web image. Press enter, you can see a contained ID is displayed. This creates and starts a container in detached mode using the nginx image. Before we make any changes, let's first verify the current state of our containers. Run the command docker ps-a. It displays all containers on the system, including running and stopped ones. Here, ps shows containers, process status. -a shows all containers, including stopped ones. Output shows all container names and their lifecycle status. Now I'm showing live lifecycle changes. First, I pause the container, then immediately unpause it, and finally restart it. This is very common during maintenance or troubleshooting. Use the command docker container pause web1 and docker container unpause web1 and docker restart web1. Here, pause freezes container processes. Unpause resumes execution. Restart stops and starts container again. Ampersands, and runs commands in sequence. In the output, you can see the container name displayed thrice. This command demonstrates lifecycle transitions during maintenance. Now that the container is running, the next logical step is to check what it is doing internally. Run the command docker logs web1. It shows the output and error messages generated by the container named web1. It is used for basic troubleshooting and diagnostics. In the output, no errors container is healthy, and if there is any errors configuration or runtime issue. If a container is running but not working, always check logs first. Now that we know the container is running, let's look deeper into its configuration and settings. Run the command docker inspect web1. Here, inspect shows detailed information and web1 name of the container to inspect. It displays complete technical details about the container, such as networking, storage, environment variables, and runtime settings. In the output, you can see large JSON formatted output with networking section with IP address and mount section for volumes. You are not expected to read everything here. Just know this command helps you find container details when something goes wrong. Now that the container is running correctly, sometimes we need to go inside it to check or fix something. Now execute docker exec it web1 bash. Here, exec run a command inside a running container. -i interactive mode. -t allocates a terminal. Web1 container name. Bash shell to open inside the container. It opens an interactive shell inside the running container, like logging into a Linux system. If execution is successful, terminal prompt changes indicating you are now inside the container. To come out, type exit. Now that the container is running, let's quickly check how much system resources it is using. Run the command docker status. Here status shows live resource statistics of containers. It displays real-time CPU, memory, and network usage for running containers. In the output we can see container name, for example, CPU usage percentage, memory usage and limit, and live updating table. If a system feels slow, this command helps us quickly see which container is using the resources. As previously discussed in the demo before, to list the images use the command docker images. It displays all container images downloaded on the system, which are used to create containers. Now that we understand single containers, let's see how we manage and scale multiple containers together. Docker compose up d scale web equals 2. Explaining this syntax, docker command line tool. Compose manages multi-container applications. Up creates and starts services. -d runs services in the background. --scale web equals 2 runs 2 instances of the web service. It starts a multi-container application defined in a Docker Compose file and scales the web service to 2 running containers. In the output, we can see containers running for the web service. Scaling improves availability and load handling. Docker Compose is lightweight orchestration. Kubernetes does the same thing, but at a much larger scale. Finally, once we are done with the container, it's important to clean up the system properly. Docker container rm-f web1. Here, rm removes the container. -f forcefully stops and removes the container. Web1 name of the container. What this command does: it stops the container if it is running and then removes it from the system. We use it to free disk space and to avoid unused or conflicting containers. It's recommended cleanup best practice for Linux administrators. What we will see in the output is container name printed on the screen. No errors indicate successful removal. Always clean up unused containers to keep your system organized and efficient. You saw the complete container lifecycle. You learned creation, management, troubleshooting, scaling, and cleanup. These concepts are directly relevant for CompTIA Linux Plus. Thank you. Now that we understand Linux security basics, let's look at how Linux decides who can log in and how. Linux uses pluggable authentication modules, called PAM. In this demo, I'll show how PAM works and how we configure it securely. PAM acts as a gatekeeper between users and the system. PAM components: PAM services, login, SSHD, sudo. PAM modules: PAM_Unix, PAM_LDAP, PAM_KRB5. Configuration file /etc/pam.d/. Stack types: auth, account, password, session. Before looking inside PAM rules, let's first see which services are controlled by PAM. Run the command ls/etc/pam.d/. This command lists PAM service files. Each file controls authentication for one service. In a typical output, you can see common auth, login, SSHD. Each file represents a service or shared PAM rule set. When a user accesses a service, PAM reads the matching file. Before making any changes to PAM configuration files, it's a best practice to take a backup. Run the command sudo cp/etc/pam.d/login/etc/pam.d/login.bach. This command copies the login PAM configuration file and creates a backup named login.bach. No output means CP runs silently on success. Now that we've backed up the PAM configuration, we can safely open the file for review or modification. Run the command sudo nano/etc/pam.d/login. The rules are accessible via the Nana editor, so the rules can be edited on the flow. What you'll see on screen is auth authentication rules. Include common auth uses centralized rules, LDAP/Kerberos. Account checks account validity. Session sets up user session. Press Ctrl+O to save and Ctrl+X to exit. Now let's test authentication by switching to another user account using PAM. Run the command su test user. This command tests whether PAM rules allow or deny login. The su command is controlled by PAM and uses the same centralized authentication rules. In the output, you see cannot change directory. This just a warning message and command prompt changes confirming the login. Now that we've seen how PAM delegates authentication, let's watch the authentication logs in real time. Run the command sudo tail f/var/log/auth.log. Here, f, follow, keeps the log open. This command shows real-time authentication events and PAM errors. In the output, you can see session open for root user. Accepted password successful login. Failed password failed attempt. IP address source of the login attempt. Press Ctrl+C to stop the command. Now, let's see how PAM controls authentication and delegates it to external services like LDAP or Kerberos. cat/etc/pam.d/commonauth. In the output, you may see lines like auth, success equals 1 default equals ignore, pam_sss.so. Auth requisite pam_deny.so. Auth required pam_permit.so. PAM acts as a traffic controller and hands authentication to LDAP or Kerberos. Next step is Kerberos configuration. In enterprise environments, Kerberos is commonly available for centralized authentication. Since it's present on the system, let's review how it's configured. Now, run the command cat/etc/krb5.conf. In the output, you can see default_realm Kerberos authentication domain, example.com. KDC server that issues Kerberos tickets. PAM uses this file when authenticating via Kerberos. Finally, let's see how a TTY login uses PAM. Run the command cat/etc/pam.d/login. In the output, you can see @include common auth, @include common account, meaning login service includes common auth. Any service that includes common auth uses centralized authentication. This means LDAP/Kerberos rules apply automatically. Troubleshooting and recovery. If something goes wrong, we can immediately restore the original PAM configuration from the backup. Restore backup if needed using the command sudo cp/etc/pam.d/login.box/etc/pam.d/login. No output files are identical. This command replaces the modified login PAM file and restores the original, known good configuration. This prevents login or authentication issues. Common issues could be wrong module order, syntax errors, missing modules. PAM is the core of Linux authentication. It is powerful but must be handled carefully. Mastering PAM gives you strong control over Linux security. Thank you. Now that we understand Linux security basics and PAM, let's move one step higher. In real companies, users don't log in locally on every server. They use centralized authentication, and today I'll show you Kerberos with LDAP, plus how we monitor and alert on login activity. In Linux, PAM plus Kerberos takes care of authentication. Groups, sudo, file permissions do authorization. Logs like /var/log/auth.log manage accounting. LDAP stores users and groups centrally, but Kerberos provides secure login using tickets, so passwords are never sent again and again. The workflow is 1. User tries to log in. 2. PAM calls Kerberos. 3. Kerberos issues a ticket. 4. LDAP provides user details. 5. Linux allows or denies access. Let us set up LDAP client. I'm working on Ubuntu Server 22.0 for acting as a client. The Kerberos and LDAP servers already exist. This is how clients are configured in production. Command 1. Install required packages. Now, first to enable centralized authentication using LDAP and Kerberos, we first need to install the required client-side packages on the Linux system. Run the command sudo apt install ykrb5 user sssd libpam sss limbs sss ldap utils. Syntax explanation. krb5 user Kerberos client. SSSD connects Linux to LDAP plus Kerberos. libpam sss pam talks to SSSD. limbs sss system can see LDAP users. These settings can be adjusted later in /etc/krb5.conf. Enter the password and in the output you can see packages install successfully. Default Kerberos version 5 realm, example.com. The realm is the Kerberos administrative domain. Kerberos servers for your realm, kdc.example.com. This is the key distribution center, KDC, that issues Kerberos tickets. Administrative server kdc.example.com. The admin server handles password changes. Remember, these prompts only create a basic client configuration. The installation is complete now. This can be verified using list. This command lists the current Kerberos tickets stored in the cache. In the output you can see the ticket cache, the default principal, validity and expiry of the ticket and the service principal example.com. PAM is not a single file, it's a framework. Here, PAM is already configured to ask SSSD, and SSSD talks to Kerberos and LDAP. So we don't hardcode passwords anywhere, everything is centralized. Key PAM idea. Login PAM. PAM SSSD. SSSD Kerberos plus LDAP. Now that Kerberos client tools are installed and SSSD is running, let's test whether a user can successfully authenticate using Kerberos. Run the command kinit student1. Here, kinit request a Kerberos ticket and student1 central LDAP user. In the output, you should see password prompt appears. No output means success. If it fails, quick demo troubleshooting. Password incorrect. Wrong Kerberos realm in /etc/krb5.conf. Time not synchronized. Kerberos is time sensitive. This command is a key demo step to prove Kerberos authentication and SSO are working. After authenticating with Kerberos, we'll verify that the ticket has been successfully issued and stored on the system. Run plist. This command shows active Kerberos tickets. In the output, you can see ticket cache location where Kerberos stores credentials, default principal authenticated user and realm, valid starting/expires ticket lifetime, KRBTGT ticket granting ticket used for SSO. This output confirms that Kerberos authentication is successful and active. This ticket is your digital identity. As long as it's valid, you can access services without re-entering passwords. Part 6. Enable and review authentication logging. Now comes accounting, tracking who logged in and when. Linux already logs authentication events for us. Now, let's review the last authentication events to see recent login activity and spot any patterns. Run the command sudo tail n20/var/log/auth.log. Here, tail n20 show last 20 lines. Enter the password when prompted. In the output, you can see Kerberos, PAM, SSH login entries like session open for user equals root. The repeated failed attempts here could be a possible brute force attack. From this file, we can answer key security questions. Who logged in? From where? And was it successful or failed? Look for accepted successful login. Sudo grep accepted/var/log/auth.log. Accepted password for Ramya from 192.168. 0.103. Failed password attack attempt. Like sudo grep failed password /var/log/auth.log. You can see failed password for the user Ramya. Repeated failures brute force sign, you can see using the command sudo grep failed password /var/log/auth.log wcl. The count, here 5. By filtering, counting, and correlating logs, we can identify abnormal behavior, brute force attacks, and authentication issues early. Authentication alone is not enough. Once logged in, authorization controls access. LDAP group mapped to Linux group using the command id student1, showing the student ID. Group-based folder or sudo access through the command ls ld secure_data, you can see the directory credentials. If Kerberos fails, always remember these 3 checks. Common issues. Time mismatch Kerberos fails. Wrong realm name. DNS not resolving KDC. Manually checking logs doesn't scale. So we automate. As a first step, let's check for failed login attempts to detect possible brute force attacks or unauthorized access attempts. Run the command sudo grep failed password /var/log/auth.log. This syntax searches for failed login attempts. The output shows suspicious login attempts. This command can be put into a script or cron job. From here, admins trigger alerts, email, Slack, or CM tools. Today, you saw how real organizations handle Linux logins securely. Kerberos plus LDAP gives us centralized control, and logs give us visibility. This is exactly the level CompTIA Linux Plus expects, and what real admins do daily. Thank you. We enabled auditing and centralized authentication. Now Linux will analyze logs automatically and alert administrators. This demo shows real-world security monitoring in action. First, I'm installing the tools we'll use for monitoring, alerting, and email notifications. Run the command sudo apt install logwatch logrotate logcheck audit mailutils y. Explaining this command, apt install installs the listed packages. Logwatch summarizes logs daily. Logrotate rotates log files automatically. Logcheck monitors logs for suspicious activity. Audit records detailed security events. Mailutils allows sending alert emails. Y autoconfirms prompts. Tools installed are Logwatch summary-based log monitoring. Logcheck real-time alerting. Audit detailed security logging. Mailutils email alerts. Once installation is completed, we need to make sure the auditing service is running, because it records every security-related event on the system. Run the command sudo systemtool status audit. Is used to check the status of the Linux audit daemon, audit. What it shows. Whether audit is running, stopped, or failed. Service start time. Main process ID, PID. Recent audit-related log messages. Press enter and the common outputs are active, running, audit logging is enabled and working. Inactive, dead, audit service is not running. Failed audit service encountered an error and needs troubleshooting. This output confirms audit daemon is running for security event tracking. Logcheck runs as its own restricted user, so let's confirm that this user exists. This ensures that real-time alerts can function correctly. Run the command id logcheck. The output shows UID, GID, and groups of logcheck user and confirms logcheck is installed properly. Now we'll use logwatch to generate a summary of SSH security events from today. This helps us see failed logins and suspicious activity at a glance. Command sudo logwatch, detail high, service SSHD, range today, output stout. Here, detail high shows maximum info. Service SSHD analyzes SSH logs only. Range today, today's logs. Output stout prints on terminal. Displays SSH security summary including failed and successful logins. To understand what logwatch is analyzing, let's look at the raw logs manually. This shows the exact failed login attempts. Run the command grep failed password /var/log/auth.log. This command searches for failed SSH login attempts in auth.log. The output shows which users /IPs tried to log in. Like, failed password for invalid user from any IPS and ports. It shows failed SSH login attempts indicating possible attacks. But here, no output as there is no failed logins. Logcheck scans logs in real time and alerts us about suspicious activity. It must be run as the logcheck user for security, so we use this command. Sudo su s/bin/bash c/usr/spin/logcheck. Here logcheck runs logcheck as logcheck user. And it prevents running as root for safety. If logcheck finds any security events, it sends an email to the administrator. Let's check our mailbox to confirm alerts are delivered. Run the command sudo mail explanation. Displays security alert emails delivered to administrator. In the output, you can see the mail version and 45 messages, 1 new 45 unread. The number before the message, 1 or 2, is the message number. To read a message, type the number and press enter. To delete a message, type D1 and press enter. To exit, press Q. In modern Ubuntu, logs are also stored in the systemd journal. We can check SSH authentication events directly from there. Run the command sudo journal ussh since today. Here, ussh SSH service logs. Since today, filter by today's logs. This reads SSH logs from systemd journal. In the output you can see failed password for invalid user. But here, you can see accepted password for Ramya. Finally, we'll automate daily log analysis by scheduling logwatch in cron. This makes sure reports are generated regularly without manual effort. Run the command sudo crontab-d and type in the editor *10****/usr/spin/logwatch, quiet. This entry runs logwatch every 10 minutes and quiet suppresses output to screen, sends report to mail. Now the cron tab is saved. Finally, if we ever need to start afresh, here's a single command that safely removes all installed tools and cleans old alerts. Run the command sudo apt purge y logwatch logcheck audit mailutils and sudo apt autoremove y and sudo rm f/var/mail/root. Here, purge removes software plus configs. Autoremove cleans and used packages. rm f/var/mail/root deletes old alert emails. In the output, you can see packages removed, terminal returns to prompt. The system is back to a clean state. For debugging, check log paths, permissions, and mail delivery. Linux can monitor itself and raise alerts automatically. Automation improves security response time. These skills are critical for Linux administrators. Thank you. Now that we know what firewalls are, let's configure one in Linux. In this demo, I'll show iptables and nftables in action. Watch how Linux blocks unauthorized access step by step. Linux firewalls inspect every network packet. Rules decide whether traffic is allowed or blocked. This protects the system from unauthorized access. Command to view active listening services. SS, TULN. TTCP sockets. UDP sockets, L listening sockets, N numeric output. You can see, the output shows active ports that firewalls control. Before making changes, always check current rules. Run the command sudo iptables lnv. Here, L lists rules. N show IP addresses. It shows all current firewall rules on the system. Output shows input, output, forward chains, policy, number of packets matched by each rule and target. This command helps us understand what traffic is already allowed or blocked. I'm adding a firewall rule. This rule blocks ping traffic. Run the command sudo iptables a input picmp jdrop. Here, a input add rule for incoming traffic. Picmp match ping traffic. Jdrop block without response. No output means rule applied. And the system will not respond to ping requests. Now that the rule is in place, let's test if it's actually working. First, I'll try to ping this server from another machine. Run the command ping 192.168.10.20. As you can see, the ping request times out, which means the firewall is blocking ICMP traffic. Connection hangs or fails, proving firewall rule works. To delete this rule, run the command sudo iptables d input picmp jdrop. Here, instead of using a to add, I use d to delete the rule. No output rule deleted successfully. Now, let's look at the firewall rules using nftable. Nftables is the modern firewall framework. Here, I'm listing the complete nftables rule set currently applied to the system, using the command sudo nft list rule set. Here, nftables firewall tool and list rule set display all firewall rules. The output displays tables, for example, init, IP, IP6, chains, and rules. Now, I'm adding a firewall rule using nftables. Run the command sudo nft add rule init filter input TCP port 22 accept. Here, first, I specify the init family, which works for both IPv4 and IPv6 traffic. Next, I select the filter table and the input chain, so this rule applies to incoming traffic. Then, I define TCP traffic going to port 22, which is the SSH service. Finally, the accept action allows this traffic. As a result, SSH connections are permitted through the firewall. Press Enter. It gives no output and the rule is applied immediately without restart. Verify the rule using the command sudo nft list rule set. In the output, if I scroll up, you can see an entry in table init filter, chain input, policy accept b, TCP port 22 accept. SSH, TCP22, is explicitly allowed and SSH must appear before any drop logic. iptable versus nftable comparison. iptable, legacy, chain-based, exam relevant. nftable, modern, faster, structured syntax. Ubuntu 22.04 uses nftables internally. Now, I'm enabling firewall logging. By doing this, UFW will record blocked and allowed network traffic. This helps us understand what traffic is being denied and why. Run the command sudo UFW logging on. In the output, you can see a confirmation message that logging is enabled. Next, we need to make the rules permanent. Now run the command sudo netfilter persistent save. This command saves the current iptables and nftables rules. So, even after a system reboot, the firewall rules will still be applied. Without this step, all firewall rules would be lost after restart. Now I am checking the current firewall status and rules, using the command sudo UFW status verbose. You can see in the output, firewall status, active/inactive and allowed and denied rules. Finally, as best practices, follow least privilege. Test rules before production. Enable logging. Automate firewall deployment. Today we configured Linux firewalls using iptable, nftable, and UFW. These tools help secure Linux systems effectively. Practice these commands for Linux plus success. Till now, we have worked with iptables and nftable, which are powerful but complex. Now, let's simplify firewall management using UFW and firewalld. These tools make firewall configuration faster, safer, and beginner-friendly. To begin with, we know that the Linux firewalls control incoming and outgoing network traffic. They block unauthorized access and allow only trusted connections. Instead of allowing everything, we explicitly decide what is allowed. Let's do a recap of iptables and nftables from the previous demo. Iptables and nftables work at a low level inside the kernel. They provide powerful control but are difficult to manage manually. But now, instead of writing complex firewall rules, I'm using UFW, Uncomplicated Firewall, which is the simplified firewall tool in Ubuntu. UFW makes firewall management easier. UFW is not always active by default on Ubuntu server. Now, before making any changes, let's check the current firewall status. I'll run the command sudo UFW status to see whether the firewall is active or not. Based on this output, we decide our next firewall action. The output says UFW is inactive now and no traffic filtering is happening. Since the firewall is currently inactive, the next step is to allow essential services first. For a server, the most important service is SSH. Run the commands sudo UFW allow SSH, sudo UFW enable. First, I allow SSH traffic by service name, so UFW automatically opens port 22. We allow SSH because it is the main way we access a Linux server remotely. If SSH is blocked and we enable the firewall, we may lose access to the server. So SSH is always allowed first to avoid locking ourselves out. Next, I enable the firewall, which activates all the configured rules. After execution, you can see UFW warns us that enabling the firewall may affect SSH. Since we already allowed SSH, it is safe to proceed. Press Y, and the output confirms firewall is active. Now that UFW is enabled, let's set the default policy for incoming traffic. We want to deny all incoming connections by default, and then allow only the services we trust, like SSH, which were already allowed. Run the command sudo UFW default deny incoming. Here, default set default policy and deny incoming block all incoming traffic. No immediate output change. You can see, default incoming policy changed to deny. Now, the firewall behavior becomes more restrictive. But outgoing traffic is still allowed by default, so the server can reach the internet. Now, I'm resetting the UFW firewall back to its default state, and after resetting, I must re-enable the firewall and allow required services again. Using commands sudo UFW reset, sudo UFW allow SSH, sudo UFW enable. This command deletes all rules, including allowed services, and resets UFW to default state, inactive, and always allow SSH to avoid lockout. Now, the system returns to a clean firewall configuration. Proceed with yes. And you can see rules updated in the output. As a first step, we need to understand that firewalld is zone-based, which means different rules can apply depending on the network you're on. Before making any changes, let's check which zone is currently active on our network interface. Run the command sudo firewall cmd get active zones. In the output, you can see public interfaces ENS33, meaning the public zone is applied to interface ENS33. Now that we know the active zone, let's allow web traffic. Run the command sudo firewall cmd permanent add service equals http. We use the permanent option so this change survives system reboots. This ensures HTTP requests can reach our server anytime. After execution, if you see a warning and a success message, the rule was added permanently. After adding a permanent service, we must reload firewalld to apply the change immediately. So, run sudo firewall cmd reload. You will get a success message as output. Firewall rules are now active. Only allowed services can communicate. Blocked traffic is filtered. We can check the firewall status using the command sudo UFW status verbose to confirm it's active and that SSH is allowed. But shows inactive here as we have given a reset in the before steps. Next, we will see active services and ports in the current zone by executing the command sudo firewall cmd list all. The output shows which services are allowed in the active zone. Here we see SSH and HTTP are permitted, which is exactly what we configured. We can also check the open ports through the command sudo ss-tuln. This command shows the list of listening TCP/UDP ports on the server. Now, notably, for troubleshooting, most firewall issues are due to missing rules. Always verify firewall status first. Logs help identify blocked traffic. Next, while switching between firewall tools, iptables and nftables are backend engines. UFW and firewalld are management layers. Use only one firewall manager at a time. Finally, as best practices, always allow SSH before enabling firewall. Use UFW for simplicity. Review firewall rules regularly. Today, we simplified firewall management using UFW and firewalld. These tools reduce complexity while improving security. This knowledge is important for exams and real-world systems. Thank you. Up to now, we configured security manually. In enterprise environments, automation saves time and reduces mistakes. In this demo, we'll automate security scans and firewall fixes in Linux. Alright everyone, now that we understand what could go wrong with a system, let's see how Linux can check itself automatically. We'll use a tool called Linus to scan for security weaknesses. Linus is a popular open-source tool for auditing and hardening Linux systems. Run the command sudo linus audit system. This command runs a full security audit on the system. When Linus runs, it scans everything, from firewall to users to malware, and gives a hardening score. Then gives a summary at the end. When prompt t equals d, give the password. You can see the scan is running. At the end, the output gives a summary showing hardening index, 63. Tests performed, 264. Plugins enabled, 1. Next, we'll automate our Linus scan by creating a script. Let's open a new file in /usr/local/bin. Run the command sudo nano/usr/local/bin/security_scan.sh. The nano editor is open and type the script content. #bin/bash. Linus audit system, quiet/var/log/security_scan.log. Sudo UFW allow SSH. Sudo UFW enable. Here, Linus audit system runs the full system audit. Quiet minimizes extra output. /var/log/security_scan.log saves the results to a log file for later review. By including of allow SSH in the script, we make sure the firewall can be safely enabled automatically without locking ourselves out, which is a key step in automated security remediation. Save and exit. Now, this script will run Linus quietly and store all scan results in a log that we can check anytime. Next, make the script executable by running sudo chmod +x/usr/local/bin/security_scan.sh. Now, you can run it anytime with the command sudo /usr/local/bin/security_scan.sh. This command runs the scan silently and stores results in a log file. How simple, with just a script, you can now run the scan. Now that we have our security scan script ready, we don't want to run it manually every day. Cron allows Linux to run tasks automatically at scheduled times, which is perfect for regular security checks. Open a cron table through the command sudo crontab-d and add a cron entry 02***/usr/local/bin/security_scan.sh. This tells Linux, run our scan script every day at 2 a.m. automatically. No one needs to type anything. Now give Ctrl+O to save and Ctrl+X to exit. Now the system will scan itself automatically every night, store logs, and help us keep track of security issues without manual effort. Rerunning Linus manually after scheduling or after the first cron run lets us confirm the automated scan and firewall fixes worked correctly. So, repeat the Linus scan by executing the command sudo linus audit system. Now, check logs by running cat/var/log/security_scan.log. And you can see two executions, one for 15 seconds and another for 16 seconds. Remember the best practices to follow. You always log automated actions. Test automation before production use. Use simple scripts. Review reports regularly. Linux can secure itself using automation. This approach is widely used in enterprises. For Linux Plus, remember automation improves security. So far, we've understood cryptography concepts in theory. Now let's apply them on a real Ubuntu Linux server. Watch how we secure files and communication the way Linux administrators actually do. Before we can encrypt anything, we need a secure key. So let's start by generating a strong symmetric encryption key on this Linux system. Here, OpenSSL generates a secure random key. This file must be protected. If someone gets this key, encryption is broken. Run the command OpenSSL rand-base 6432 greater than symm.key. Here, OpenSSL rand generates random data. -base 6432 strong, readable format greater than saves the key to a file. Output explanation. No screen output. A file called symm.key is created. Now that the key is ready, the next logical step is to use it. Let's encrypt a file and see how Linux protects data at rest. Run the command. OpenSSL enc-256-cbc-salt-in demo.txt-out demo.txt.enc-pass file symm.key. Here, enc encryption tool. -aes-256-cbc strong symmetric algorithm. -salt adds randomness. -pass file reads password from key file. Now I'm encrypting a file using AES-256. Notice I'm not typing a password, I'm using a key file. This is safer and commonly used in automation. In the output we are getting a warning that ITER or PBKDF is better. OpenSSL is warning you that it used an old, weak key derivation method. It still encrypted the file and demo.txt.enc is created. The encrypted file is unreadable text. Verify using. Encryption protects confidentiality. But how do we know the file was not changed? That's where hashing comes in. Encryption hides data, but hashing proves integrity. If this file changes even slightly, the hash changes. This is how Linux detects tampering. Run the command. SHA-256-SUM demo.txt. Here, SHA-256-SUM generates a SHA-256 hash. Output explanation. Long hexadecimal value. Remember, same file equals same hash. Modified file equals different hash. So far, we've secured files. Next, let's look at identity and trust, which is where digital certificates are used. Run the command. OpenSSL req-new-x509-days 365-nodes-out demo.crt-keyout demo.key. Here, req certificate request. -x509 self-signed certificate. -keyout private key file. -out certificate file. Here we create a self-signed certificate. Certificates are used for identity and secure communication. Private keys must never be shared. Now it prompts for certificate details, give country name and province name and leave the remaining blank. Now this creates demo.crt and demo.key. Once identity is established, the next step is secure communication. Let's transfer an encrypted file over an encrypted channel using SSH. Run the command. scp-demo.txt.enc ramya at remote-server/home/user/. Here, SCP secure copy uses SSH encryption by default. SCP uses SSH underneath. That means authentication, encryption, and integrity are automatic. No extra encryption setup is required. If prompted, give the password. In the output, transfer progress is shown and file arrives encrypted on the remote host. SCP says you pointed to a directory. So far, we encrypted files using OpenSSL. Now let's look at GPG, which is commonly used for files and emails. For email and multi-user encryption, Linux uses GPG. GPG supports encryption, signing, and trust verification. Most crypto errors happen because of wrong permissions, missing keys, or incorrect paths. Here I'm using symmetric encryption with AES-256, just like before. GPG-symmetric-cipher-algo AES-256 demo.txt. Explaining the syntax, GPG GNU Privacy Guard tool. --symmetric uses one shared secret. --cipher-algo AES-256 strong encryption. Demo.txt file being encrypted. In the output, GPG prompts for a passphrase, enter. And renter, and if asked give yes to overwrite. A new file demo.txt.gpg is created. Original file remains unchanged. Now you've seen how Linux secures data from start to finish. From key generation to encrypted transfer, every step follows a security principle. So far, we've understood encryption, hashing, and secure communication in theory. Now I'll show you the exact Linux tools you'll use in real systems to protect data. Watch how a few commands handle encryption, keys, certificates, and automation. Let's begin. Now that we understand symmetric encryption, let's actually encrypt a file using OpenSSL, which is a standard Linux cryptographic utility. Run the command. OpenSSL enc-aes-256-cbc-salt-in data.txt-out data.enc. Here I'm using AES-256, a strong symmetric encryption algorithm. The -in option specifies the original file, and -out creates the encrypted file. The -salt option adds randomness to make password attacks harder. After execution, you'll be prompted for a password. This same password is required to decrypt. If you lose it, the data is gone. There is no recovery. No output on the screen means the command succeeded. A new encrypted file data.enc is created. Verify this using ls, which shows data.enc listed. Now that the file is encrypted, let's decrypt it and verify the data using the same symmetric key. Run the command OpenSSL-ENC-256-CBC-D- in data.enc-out-data.dec. The -d option tells OpenSSL to decrypt. Data.enc is the encrypted input file, and data.dec is the decrypted output file. The same password used for encryption must be entered again. If the password is wrong, OpenSSL throws a bad decrypt error. That's expected behavior. Now the decryption is completed and you can verify the file data.dec using ls. Now we'll move from symmetric encryption to asymmetric encryption by generating a GPG key pair. It covers key generation, key management, encrypted storage. Run the command gpg-full-generate-key. This command creates a public key and a private key. The public key is shared to encrypt data. The private key stays protected and is used to decrypt. You are asked to choose key type RSA and RSA. Choose key size 3072 or 4096. Set key expiry optional and yes for prompt. Enter name, email, and passphrase and give OK. When prompted, enter the passphrase. Linux shows messages like public and secret key created and signed. To verify revocation certificate, run the command ls-l/root/.gnupg/openpgp-revox.d/. This directory stores revocation certificates for each key. If the .rev file exists here, GPG successfully created it. When executed, you can see the .rev file. This file is your emergency brake if the private key is exposed. If this file is missing, you cannot revoke the key later. Verify the public key existence using the command. The output says, a key is listed in the output and you can see RSA 3072-2026-2-10E, expires 2026-2-11. Now that we have a public key, let's encrypt a file for a specific user using GPG. The first command creates a file, which will be encrypted using the recipient's public key. The second command encrypt the file using asymmetric encryption with GPG. Here, the -e option means encrypt. The -r option specifies the recipient, identified by their email or key ID. Only the matching private key can decrypt this file. After execution, no terminal output equals encryption succeeded. Linux creates secret.txt.gpg. Only the matching private key can decrypt it. Verify this using ls-l secret.txt.gpg. If this file exists, encryption worked. Now let's generate a hash to prove the file has not been modified. Run the command sha256 sum data.txt greater than data.hash. sha256 sum calculates a sha256 hash of the file. The greater than symbol redirects the output into a file called data.hash. This hash acts like a digital fingerprint. Verify this using ls and cat data.hash. In the output you can see a long string, which is the digital fingerprint of the file. If even one character in data.txt changes, this hash will no longer match. Now we'll verify the file integrity using the hash we generated earlier. Run the command sha256 sum-c data.hash. The -c option means check. Linux recalculates the hash of the file and compares it with the stored value. If both hashes match, the file is unchanged. In the output, you can see data.txt, OK. OK means the file has not been modified since the hash was created. If it says failed file was altered. Hashing doesn't encrypt data. It proves the file was not modified, even by 1 byte. This is critical for downloads, backups, and audits. To create certificates or enable TLS, we first need a private key. To generate private key, run the command OpenSSL gen RSA-out server.key2048. This command generates a 2048-bit RSA private key. The private key is saved in the file server.key. This key must be kept secret. If it's leaked, security is broken. No output on the screen. Success. A new file server.key is created. The file contains sensitive cryptographic material. Verify this using ls-l server.key, which lists server.key. Now that we have a private key, we'll create a self-signed certificate from it. Open ssl-req-new-x509-key server.key-out server.crt-days 365. This command creates a self-signed x.509 certificate. It uses the private key in server.key and outputs the certificate to server.crt. The certificate will be valid for 365 days. Open SSL prompts for certificate details. Country. Organization. Common name, hostname or IP, important here. These values identify the server. The common name is the most important field. The certificate is created, which can be verify using the command ls-l server.crt. You can see a .crt file. The .crt file is the public certificate, it's safe to share. Self-signed certificates are encrypted but not trusted by default. Browsers and clients will warn unless a trusted CA signs them. Next, let's verify what's inside the certificate we just created. Run the command. Open SSL x509-in server.crt-text-no out. This command reads the certificate file and displays its details. The -text option shows the certificate in human-readable form. The -no out option prevents the encoded certificate from being printed. In the output, you can see validity start and expiry date, subject server identity, common name, issuer who signed the certificate, same as subject for self-signed. Encryption protects data, but certificates protect identity. Without identity, secure services cannot function. Services like HTTPS, LDAP, and VPNs don't just encrypt traffic, they must also prove who they are. If certificates expire or are invalid, services fail. Clients trust the service only if the certificate is signed by a trusted CA, matches the server name, is valid, not expired or revoked. Instead of passwords, Linux uses SSH keys for secure authentication. We will generate SSH key using the command ssh-keygen-ted25519. Here, ssh-keygen creates an SSH key pair. The -ted25519 option selects the ed25519 algorithm, which is fast and very secure. When prompted, enter the passphrase. This generates one private key and one public key. After this, you will get key fingerprint, which is a short, unique hash of the public key, and randomart image, which is just a visual hash/representation of the fingerprint on the screen. You can verify using the command ls-l/.ssh/. Remember, SSH authentication works by proving you own the private key. The server never sees your private key. Next, I'll copy my public SSH key to the remote server so I can log in without a password. ssh-copy-id ramya at server. SSH copy ID sends my public key to the remote server. It appends the key to the server's authorized_keys file. After this, the server can recognize my private key. When executed, you are prompted for the user's passphrase, and in the output you will see number of keys added, 1. Remember, file permissions must be correct, or SSH will ignore the key. Remember, SSH refuses weak permissions. That's intentional. Keys and encryption matter only when data moves. SCP proves that file transfer is encrypted and authenticated using SSH keys. Now I'll securely transfer a file to a remote server using SCP. Run the command scp-data.txt user at server/tmp. Here, SCP stands for secure copy and data.txt is the local file. User at server/tmp means copy it to the /tmp directory on the remote server as that user. The transfer is encrypted using SSH. In the output, you'll see something like data.txt 100% 2812.3 kilobytes per second 0, 0. This shows file name, transfer progress and speed, finally completion status. Verify using SSH ramya at server. Passwords are weak. SSH keys are stronger and auditable. SCP uses the same encrypted tunnel as SSH. If permissions are wrong, SSH will refuse the key. That's security, not a bug. Finally, I'll automate file integrity checking by generating a cryptographic hash using a simple bash script. Create a script. nanointegrity_check.sh. And edit it. Shebang. SHA-256 some important.log greater than important.hash. This script can run via cron to detect tampering automatically. Linux Plus expects you to understand this workflow, not memorize cron syntax. Make it executable. chmod plus x integrity_check.sh. Run the script by executing /integrity_check.sh. If needed, you can verify the automation using ls-l important.hash. Automation in Linux means repeatability. Scripts are how we make security checks repeatable. Common errors to call out. Permission denied, wrong file ownership. Bad decrypt, wrong password or key. Untrusted certificate, CA not installed. SSH key ignored, wrong permissions on /.ssh. You've now seen how Linux handles encryption, keys, hashes, and certificates. For the exam and real systems, remember, few tools, used correctly. Practice these commands. Security failures usually come from misuse, not missing tools.